Remo, can you mute your microphone? Good morning to everybody, and welcome to this plenary session, morning plenary session of MG16. And I will introduce the first speaker this morning, Selma Demink, that she will talk about the massive binary stars in the era of gravitational wave astrophysics. Please, Selma, go ahead.
Okay, thank you very much. It's an honor to talk and a pleasure. I think that talking about stellar physics fits very well in a meeting on gravity, because gravity is what drives how stars work and how they fight and what sets their final fate. So I took a slightly broader title here today, but I will talk about the stars that lead to gravitational wave sources today. Let me briefly take you back in time and discuss the excitement that I think all of us shared 5-6 years ago when we saw the first detection. If I can move my slides. So what did we know about black holes before 2015? Well, observationally, we didn't know about many stellar mass black holes. The only ones we knew about were black holes that have a stellar companion feeding them, mostly detected in X-rays. And the masses of these black holes were determined because we saw the other star moving around it using Kepler's law. And so in the background, you see a graph that is actually an outreach image from the LIGO and Virgo collaboration. And the purple dots indicate the masses of the black hole known so far. So the arrow bars are not indicated, it was meant for public outreach. The y-axis shows how massive they are in solar masses, and the x-axis doesn't have a meaning, they're just grouped together. But I briefly wanted to show you this. This was, of course, the excitement in 2015 or 2016 for most of us when we heard about the first detection. And so this has been fantastic in so many ways. Clearly led to the award of the Nobel Prize. But for astrophysicists, the big excitement, and physicists alike, the big excitement was, is this very different from the black holes we know so far? Right? So the two incoming black holes were much more massive than the black holes the stellar mass black holes that we knew so far. That was the first event. Were we lucky? Surely, we were very lucky. But it turns out these massive black holes are quite common. So this is a similar picture, also showing the neutron stars now. Again, the x direction doesn't have any meaning, but the y direction shows you the mass of these objects in solar masses. Again, as outreach, there's 2 question marks there for objects that have very big arrow bars. So this was the situation back in 2015. These are the first 3 detections. We have here on the left the very massive first detection that we had. But the second and the third detection were already much more normal, if what we knew before was actually normal. And so it does indicate that these gravitational wave black holes are part of a population that is probably a similar population as the ones we see in our galaxy, or not a completely different beast, let me put it this way. But they are more massive. And so this picture continued. This is after the second observing run, and the third, halfway the third observing run. So this is fantastic. This is where we are today. So one way this picture is being named is, people call it the stellar graveyard. And it makes it very interesting because maybe this is a way we can learn about how massive stars work. We don't know much about massive stars, especially not the very massive stars that lived earlier in the universe when the conditions were quite different than in our own galaxy. And some of these black holes are probably probes and remnants of these first black holes. So this is not the stellar graveyard. There's many black holes here that formed from the merger of 2 black holes. So let me take out, I did this by hand, so you see it's not very nicely done, but I tried to block all the black holes that were mergers of 2 black holes, at least where we know this. And so what we're left with is a picture with black holes that could be the remnants of stars. I cannot exclude that there's still a merger in there, but so this is the picture that might tell us something about how massive stars die and the remnants they leave behind. So there is 2 features in this diagram. They're not overly obvious, but they have been discussed. And so there are these 2 features. So let me start with the lower blue bar. And so it seems that there is a reduced number of compact objects between about 2 and 5 solar masses, maybe 3 and 5 if you want to be safe. There's at least one object in there, and maybe more claims. So for a long time, people have been discussing, is this a gap that exists? And that gap was an empirical gap. It is not a solid theory predicting this, although we do have models that can reproduce this, but it was not predicted by theory. It was just a gap that was seen, and it wasn't clear whether these were biases or there's really less systems. We were very excited about this because this lower mass gap can probably tell us about how stars explode, and when they explode, how much mass falls back. So I'm not going to talk about the lower mass gap. I want to talk to you about the upper mass gap, especially if you have never heard of it. I would like to introduce you what it is and why we're so excited about it. And so that's the main topic of today. The location of the upper mass gap is a matter of debate, but it's a theoretical prediction, and it should be around 45 to 120 times the mass of the sun, although there's different claims there. Okay, let me take you one step back. Let's briefly ask the question, how did these black holes form? And how did they come together in pairs that could actually merge? And so this would be the topic of a different talk, but I don't want to leave this out. It's not enough to make one black hole. You need to make 2 black holes that are very close distance to each other, so that gravitational wave radiation is actually efficient enough to drain angular momentum from the system and merge them, at least within a Hubble time, so that we can see their radiation. So there's many ideas for how these may form. And so I don't have time to go through all this, but I want to show you the diversity of ideas. And so there's a whole class of ideas that think about how stars in binaries interact with each other. There's a whole class of ideas on the right that consider the dynamical processes, basically just orbits and near passages. And there's a subset of ideas that think about very gaseous environment where you might have friction. And so just to give you an idea, the most popular, no, that's not right. The first idea that have been proposed, and I think the most studied today, also it's still full of uncertainties, is what some people call the classical channel or the common envelope channel. And so the idea is that the 2 black holes are remnants, or neutron stars in this case, are the remnants of stars that were part of a binary system that was initially very wide, but at some point, one of the stars engulfed the other star, or the black hole, or its core, into its envelope. And this would shrink the cores and compact objects closer together to distances small enough for gravitational wave radiation. Skipping over a lot of details there, but that's the main idea. So you eject the envelope of one of the stars, and what you gain is that you can shrink the system. Another very popular idea is that these black holes are remnants of stars that form in star clusters. And these black holes would sink to the center, eventually form pairs. And because the densities are so high, it's actually quite likely that a binary pair has a close interaction with a third star or third compact object. And each time these near collisions happen, you can shrink this binary a little bit, ejecting the third star again with extra energy. So this is a very popular idea. And there's many more. People discuss how systems of 3 stars can have very long resonances, can drive together the inner binary. There's an idea that you start with 2 stars that are very close. This is actually one we proposed, and that these stars have very different lives that are so distorted that they stay very compact and form massive black holes. And last, I have a nice picture here for what if they're stellar mass black holes in the centers of galaxies in very gas-rich disks. So I guess we are learning a lot also from the insights that we have from how planets form around a star, but this is a disk around a supermassive black hole, so a scaled up version of this. But if there's stellar mass black holes that get caught in these disks, they may be able to find each other, and the dynamics will be assisted by the drag they feel from the gas. Okay, so that will be a different talk, but just to highlight, there's plenty of ideas how they form. So this is a bit daunting in a way, or exciting, depending on your moods, but it's daunting in a way because all these processes here, they have many uncertainties and detailed physics that we don't fully know. And with so many ideas out there, how do we truly learn what is right and what's happening here? How do we learn physics from this? And so I think this is the question we should still be asking. What is the most fundamental lessons that we will learn about stars from gravitational waves? You may have other interests, but I'm interested, what can we truly learn about stars? And I don't want to offend any of my colleagues, but this is astrophysics, and astrophysics is full of uncertainties. So we have model predictions, but often these model predictions are not so solid. And so as soon as there is a constraint, our model predictions, we may consider these uncertainties and our model predictions would change. And so this is not a very helpful, but it is the reality that we are dealing with. And so I feel the theoretical predictions have a little bit of a jelly pudding behavior. As soon as you say, this is a constraint that needs to be met by observations, there's often a lot of freedom in the models that they can move around. And so this is, for example, because of uncertainties in how stars lose mass, how much mixing they have, nuclear reaction rates, how stars explode, if stars exchange mass, how much, and how does this common envelope work? And so there's many more uncertainties. But I don't want to paint this very negative picture. I actually want to show you that there is a cherry in this pudding. So there is a viscous part of these models that makes a prediction that will not change easily. And so that's what we're looking for. What are the most solid aspects of the predictions of these models that the different channels have in common and that will not move, or if they move, we can learn physics from them. And so I want to argue that the cherry here has to do with a process called pair instability. So I'll briefly introduce you to this in case you have not heard of this. So apologies to the experts, I will probably not tell you something new. And so the pair instability mass gap has to do with this picture. We're thinking about very massive stars. They're very hot, and most of their pressure actually comes from the photons, the radiation that is supporting them. Some of these massive stars get so hot that photons may have so much energy that some of them would exceed the rest mass of an electron-positron pair. And so if this happens, it becomes possible that we get a conversion from photons to electron-positron pairs. So that's not great for the star, because these photons were holding up the star against its gravity. And so this would happen, well, formally at a temperature of 1.2 times 10 to the 10 Kelvin. But in practice, this already happens at 10 to the 9 Kelvin because of the high tail of the energy distribution. So if this happens, the energy of the photons is converted in rest mass. And so the star loses support. And so it turns out that this makes stars unstable. So which stars do this? This is a classic diagram that would be part in any stellar evolution course. I try to simplify it a little bit. So it shows the temperature that we would have in the center of a star on the vertical axis, central density on the horizontal axis. And I indicated the region where these pairs can form. Now stars, when they evolve, simplifying things a lot, their center, the temperature in the center increases and the density increases, and they roughly follow an evolutionary track with roughly this slope. There's many excursions when you show this in detail, but let me simplify it for today. So less massive stars, they run almost parallel to this. And as you may know, less massive stars may hit at some point get cores so compact that electron degeneracy starts to support them. And this happens often when they're still made of carbon oxygen, and these are stars leaving their lives as white dwarfs. So the sun would be on this lower mass track. So more massive stars is what's needed to hit this region, this pair instability region. Let me show you this in a cartoon. So there's many people that have worked on this, but the cartoon is for my student Matteo Renzo, so I hope this helps to explain. So we have a very massive star, and late in its life, it would reach these temperatures over 10 to the 9 amperes are created. So what happens is that the support for the star diminishes, and the star contracts, but the pressure support doesn't go up enough, or stated a bit more precisely, the equation of state softens. And so what happens is that the star starts to collapse. When the star collapses enough, the temperature rises, and most of these stars still have oxygen in their core when this happens. And the temperature reaches values high enough where oxygen can ignite it in an explosive fashion. If that happens, depending on the masses that we have, if you ignite oxygen explosively, so much energy can be liberated that you completely disintegrate the star. And so this is what we call a pair instability supernova. This is fascinating because it's a very massive star that suddenly leaves no remnant at all. But that's not great if you do gravitational waves, because we would like remnants. But it's very interesting that these stars would explode completely. Not all stars do this. If a star is slightly less massive, we would go through the same process, but the explosion would not be powerful enough to unbind the star. And so what would happen is that there is still a small explosion leading to a shock wave, and it would expel some of the outer layers, but not enough, and not all oxygen would be burned. And so what can happen is that the star that is there is then later contracting. It's radiating neutrinos, which is also exciting, but it would contract and it would close this loop. And it may actually go through this circle multiple times, maybe 5 times or so, each time ejecting mass. But at some point, the nuclear fuel, it's running out of this nuclear fuel. And at the last time it does this loop, when it contracts, it can no longer heat up again. And we are left with a black hole. And so the predictions differ a little bit, but it's roughly black holes up to 45 solar masses you get from this. There's another exciting possibility is that if the star is very, very massive, that the first time at step 3, the oxygen ignites, but the star is so massive that it cannot fully explode. And so there's too much binding energy. And so you would lead to a black hole. So what you see on the right is already a mass spectrum. It shows that we would get black holes below about 45 solar masses and above 140 solar masses, but black holes in the middle are not allowed, at least not as the remnants of stars. So I told you that massive star evolution is very uncertain. It's astrophysics after all, but there's something remarkable. And it turns out that this prediction is very solid. In fact, it's the most solid prediction that I know for very massive stars at the end of their life. And I'll first try to show you and give some, intuitively, we can already understand it. So whether or not a star goes through this pair instability regime really depends basically on its weight and internal structure in a very late stage of its life. And it doesn't really matter how the star got there, but it's the conditions at that time which will then decide what the black hole mass will be. And the weight of the star is crucial in this. And the weight of the star is also crucial in deciding on the black hole mass. And how the star gets to this point is extremely uncertain. But if it gets to the point, the location of where you can form black holes is very solid. So we investigated this in more detail, following up on work of others. And I should especially credit Stan Woosley, who has been, I guess, the main driver of this field. And in all honesty, I was always very skeptical when he gave talks and quoted his results in 2 or 3 digits of precision. But I've gotten more respect for this later. So let me show you, we can do experiments taking numerical simulations where we follow the evolution of stars, or at least the course of stars. And so what we did here is a survey of stars with different helium masses and different composition, or metallicity, as we astronomers say. And so each little rectangle in this diagram is one of these stellar models. And so what you see here is 3 regimes. There's regimes where we have core collapse, really forming black holes. regime where we have pulsations, and a regime where there's no black hole at all, apparent stability. So the color is indicating the black hole mass. So this looks like a mess possibly, but let me show you the same data in a slightly different diagram. And then I think there's something remarkable. So I'll show you in this diagram, and I want you to pay attention on basically mostly the y-axis. So on the horizontal axis, I'll show the core masses, but the y-axis shows the black hole masses. And so there's
Selma, 10 minutes.
Yeah, thanks. So there's a lot of curves in this diagram. They assume different composition, but what stands out is that these curves really are very close to each other and overlap. And that's not the most important point. The most important point is that the maximum of each of these curves is within a few solar masses, the same value. Let me briefly help you guide you through this diagram. So on the left, we have stars that go through direct collapse. You can see that the core mass and the black hole mass are sort of one-to-one relation. And then on the right-hand side, we have no black holes. That's where these parent stability supernova leave no remnant. And in the middle is where we go through this circle of pulsations and stars lose mass. So it turns out that the maximum mass of these black holes is basically independent. All these lines, they show the same maximum mass within a few solar masses. I don't know if I can fully help you to appreciate this, but there's almost no prediction I know for massive stars at the end of their life that is certain to about 10%. But this seems to be one. So here we varied the composition of the stars. We also varied how much mass they lose, which is somewhat similar. And in the left diagram, you still see that the maximum between these curves is very similar, just a few solar masses. We also varied how to treat mixing, and it's only a few solar masses difference. So this is great. And I would argue this is one of the sort of viscous parts of our jelly pudding, or a prediction that will not easily move. And these are the kind of predictions where we can learn something. Now, it's not true it cannot move at all. If you play with stellar evolution codes, it can change with the reaction rates. And I'll show you that in a different diagram. So in this diagram, it turns out that the nuclear reaction rate that is most solid is that has most impact is the reaction rates that converts carbon into helium. Right? It's unfortunately, it's one of the most important reactions in stellar evolution, but it's also a very uncertain one. There's the resonance around the temperatures that where this happens in stars. And so what you see in this diagram on the x-axis is what is the assumed assuming 1, 2, and 3 sigma lower, or 1, 2, and 3 sigma higher. And on the y-axis, you can see what black holes form. And so we form black holes to about 45 solar masses. Then there is no black hole formation, and at about 140 solar masses, they start again. And so there's a recent paper from Mehta et al. Oh, sorry about that. That's doing this with slightly updated mass loss rates, finding slightly different values, but similar. Yeah. Okay. I haven't stated this very clearly, but there is at least one black hole that violates this prediction. So what about this? How is it possible that we make black holes with forbidden masses? Now, there's many ideas here. Still astronomers are full of ideas. And this overview I took from a review by Rob Farmer. So how can you make black holes that are bigger and that have forbidden masses, bigger than the lower edge of the gap? So there's different ways to do this. You can think of things to do before you form the black hole. Namely, you could move the gap, or you could avoid the gap. I'll expand a little bit in a moment. And you can do things after you form the black hole. You can maybe accrete onto a black hole, or, and this is the most popular idea, you can merge black holes together and make new black holes. For LIGO to still find where the gap is. Even if the gap is not completely empty, we might still find the edge of the gap. I had the references earlier in my slides for this. Let's start with multiple mergers. I think it's the best candidate to explain the massive events. It would be rare, not so rare that we never see those events, but so rare enough that we would still be able to find where the gap is. And I would argue that these two are also rare, but I'll show that in a moment. So the idea is that you form black holes separately and that they find each other later. And one place where this could happen is in a very massive star cluster. And this is challenging because if you merge two black holes, there's usually a recoil, and it's not so easy for these black holes to actually stay in a star cluster and merge with a third black hole or even a fourth. But this should possibly be possible at low rates in the most massive clusters, or even better in nuclear star clusters. So this should not be very common. And if this happens, there's very clear signatures for the mass ratio and spins expected. So if this is the answer, we can most likely distinguish these. And second idea is what you can do after a black hole formed is you may be able to accrete onto a black hole. Really increase the masses of black holes. And specifically, if you do this, in the case of one, you widen the systems and it would not likely to make gravitational wave events. There's other people that have considered the possibility for black holes to accrete, especially if they sit in a very gaseous disk. And it's also hard to feed black holes to significant rates. So I would say this is hard, and even if if you have a core that is too massive, it will undergo this pair instability phenomena. If the core is less massive, you'll just make a core collapse. So, so if you try to think of a star that has a core below the edge for stability, and it would make a black hole, it would not make a very massive black hole, unless it still has a big hydrogen envelope that would also fall into the black hole. So the trick is for the core to be in the regime for direct fallback black hole formation, but still have a hydrogen envelope around. My guess is that this is very rare and hard to do, or to retain a big hydrogen envelope so long in their life, especially if you want to bring two black holes close. But there's definitely people that are more optimistic and have thought about ways on how to do this. And I would say the most promising way is maybe that you have a star where this hydrogen envelope is in a way replenished because you accrete new stars onto this. So that's stellar mergers. The other idea is that you go for stars with very low mass loss rates. And there's references here. So I would argue that there's different ways to make black holes in the gaps, but most ways are very rare. And the most interesting way is to move the gap. And then we can still learn physics. And as I already showed you, let's discuss move the gap. So from the location of the gap, we can probably learn about the reaction rates. I already showed that, but there's a few more references here. Another suggestion is that you can move the gap by considering the effects of rotation. So this would be interesting and possibly interesting in connection with spin measurements. But the amount by which the gap moves is not extremely large. And then the last one, but I'm not qualified to talk about this, is there's of course people that think about more exotic explanations, if I may, which are variations of physics beyond the standard model, or origins where these black holes are primordial. I'll say that I will put my money on explanations that involve stellar sources for now. Just to round up, where we proceed from here, let me remind you that this is only the beginning. At the moment, we are only halfway to having the data of the third observing run. And this diagram is also an outreach image. Oh, I'm sorry, the references got mangled up, but so we only see a small portion of the universe at the moment. With the increasing reach of detectors for 30 solar mass black holes, we should be reaching out a redshift of 10. that is basically any redshift that is relevant for black holes formed from stars. So this will be very exciting. The numbers will be insane. So we should be getting very accurate determinations of whether there is a gap in the black hole mass function. And then to round up, this will still be a challenge to distinguish all these scenarios. We will not only get the information from gravitational wave detections to answer the question, how did these black holes form? We should also think about all the other constraints that come from astronomy, from other measurements of the progenitors. And I'll just leave you with this. Thank you, everyone. Greetings from Munich. For any younger people in the audience, if you're interested in these topics, we welcome your applications there. Thank you very much.
Thank you, Selma, for your very clear talk. It gives some answer, but open more questions, and this probably is the exciting part of our job. We are ready for taking some question. I see Felix Mirabel that has a nice question for you. Felix?
Yes, can you hear me? Yes. Yes, my question is whether Eta Carina is an example of pair PP instability, and in that case, whether this process in the early universe, I mean at cosmic dawn, could have been a mechanism to generate dust very early in the universe. That is something that we observe in quasars at very high redshifts.
Yeah, thank you. I thought the question is coming from Felix. That's a very nice question, and you would not be the first to suggest it. I don't know who would be the first, but I've certainly heard Stan Woosley making this suggestion. There's other ways to explain that there's other ideas about Eta Carina too. So for those who may not be aware, Eta Carina is, I guess, the most extreme massive star that has a huge eruption, and we don't quite know why. There's other ideas that this has gone through a merger interaction, still two stars there. So I cannot say with certainty whether Eta Carina is one. The question about dust formation in the early universe is a much bigger question, right? So I think that would distract maybe too much from this. But it's one of the constraints that we need to match if we want to understand what massive stars do over cosmic time. So thanks for bringing this up.
Okay, there is two more questions. The first one from Fabian. Please go ahead. Fabian, are you still there?
Oh, thank you. I've just been unmuted. Thank you for that very nice talk, Selma. My question is, what specifically is needed from gravitational wave observations in order to better constrain some of the interesting stellar physics you've described?
Yeah, a very nice question. Well, I guess we have to work with what gravitational waves can give us. Of course, the masses, well, I don't have a good picture for this. This is a mess, right? So how would you distinguish all this? So there are differences in the mass distribution that you get from these channels. And specifically, only a few of these channels make double Newton stars, and the other channels, they are not so good at this. Apart from the masses, we're super excited to get more information about the spins. Now, the spins, as you may know, it's harder to detect. The error bars and confidence intervals are much poorer constraints, and we don't really measure the masses directly, but more the effective chi-effective parameters, or the projected and mass-weighted mass. So there's the degeneracies there, but the spins are very exciting. The mass ratios are very informative, but for most events, we have not been able to measure the mass ratio well, but there are now about 2 or 3 events with extreme mass ratios, and not all of these channels are equally good at making such extreme mass ratios. The one on the lower left, for example, is not quite good. And then the last thing, and that's maybe this picture, right? What will be fantastic to see how these distributions change with cosmic time. So if we go back in redshift, the redshift dependence will have encoded information about the delay times and when these systems formed. in a convolved way, but this is what I'm excited about. So masses, mass ratios, spins, and delay times is, I think, my list.
Okay. We have the last question from, sorry, I'm probably going to misspell your name. My apologies. Mukesh K. Vyas. Please.
Thank you. Do we expect such isolated black holes with intermediate masses in our galaxy that do not have any companion star or accretion disk? We can detect them through local gravitational lensing. Do we expect any evidence of that?
Yeah, exciting question. And I know we have colleagues that have been asking similar questions even before gravitational waves, right? It's always been exciting to think whether there's a population of intermediate mass black holes. So the population cannot be large. There's others that can would be able to comment more, but I don't think we have them here. The population cannot be large. There's not, I don't think we have direct evidence of any gravitational lensing event of an intermediate mass object. If I'm wrong, I would love to be corrected. There are claims and that are more solid of intermediate mass black holes sitting inside the center of clusters. And I know this is also a debated topic, but I think if they're sitting anywhere there, there's a good chance that they still sit in clusters today. So maybe that's a better place to start finding them.
Well, very, very exciting talk, but on their boundary condition about the evolution of very massive stars like Eta Carinae, because they can evolve in binaries, not just looking at the evolution of the single star. And the binary, we know how many they are and how many binary X-ray sources exist in the galaxy, and measure now the mass of the black hole in X-ray, in gamma ray burst, and so forth. Therefore, it will be very interesting to see the separatrix between all these traditional binary X-ray sources and so forth, and to see if indeed there exists this separation of these binary black holes, which, of course, everything will depend from the further observation. Okay.
I couldn't agree more, but it's it's not just a matter of looking at the gravitational waves. I would argue there's many stars that fail to become gravitational waves, or we cannot detect the gravitational waves because they would happen gigayears from now. But there's many products on the way, including X-ray binaries, runaway stars, contact binaries, and many exciting supernovas. I think you're hinting at similar things. Yeah.
Okay. Thank you, Selma, again. And we move to the next speaker, who is Norbert Langer. He will talk about the evolution of closed binary stars and their role in the most powerful stellar explosions. Please.
Yeah, thank you very much.
Norbert.
Let me just get this set up straight. Okay, I hope you see my screen fine now.
Maybe you can again share once more, because the same problem, we don't see full screen.
It's strange, but let me do it again then. Does this look better?
No, but yeah, probably we can keep going this way.
But you can see my slides. Mr. Chairman, is that okay? Can you see my slides fine, or is there something I should do about it? Hello?
We don't see actually the lower part of the slide. So if you try once more to share the full screen, then better.
This is really strange, not sure what I should do about it. But it worked before, so it should work again. So I share my screen. And then I go on presentation. Still the same, or is it better this time?
Still the same. Maybe you don't go to the presentation, at least we will see it not cut like this. Yeah, okay. Well, let's start this way.
Yes, I propose to go ahead because we are going to waste time.
Yeah, sorry for the problem. I have no idea what to do about it.
I'll give you 5 minutes to go, okay?
So I want to start out by, of course, thanking Remo and the organizers of this meeting to have me here. It's a very, very exciting meeting, and I'm very glad to be part of this. What I want to talk about today is something first rather simple, namely about the rotation of massive stars, and then connect this to the binary nature and to the final explosions which occur at the end of the lives of these stars. So the rotation rates of massive stars, you could say, is something easy to assess. We just go out with a telescope and investigate how fast they rotate, and people have been doing that. And over the years, I think we have been learning quite a few exciting things about this, which I would like to share with you first. What you see here on this slide is the distribution of rotation rates of early B-type stars, early B dwarfs, that is. So that stars between, say, 8 and 15 solar masses. This has been measured from the VFD flame survey of massive stars, and what you see is that the probability density as function of equatorial rotational velocity is bimodal. So we have a group of stars here in this regime which rotates rather slowly, which consists of about 30% of the sample. The sample is 300 stars here with high quality spectra. It's a really very good database. And then the bulk of stars rotates at maybe 300 kilometers per second. And you see there's a gap in between where there's few stars. What we further see is that there is a tail of stars rotating rather rapidly, where with 500 kilometers per second, we approach the critical rotation of the stars. So I would claim that there is 3 components here in this distribution. And so we can look at the A stars as well. Stars of lower mass, you see the mass scale here. Again, we have the equatorial rotational velocity here, and color-coded you see the probability density again. Let's just look at stars, say, above 2 solar masses in this regime. What you see is a similar pattern. You see a group of slowly rotating stars here. Then you see a gap, then you see more rapidly rotating stars. And finally, you see a distribution, a tail of the distribution towards very high rotational velocities. So I think these 3 components prevail throughout the upper mass range, the mass range of upper main sequence stars. There's further evidence from looking at young star clusters. So this is color magnitude diagrams from young star clusters in the Magellanic Clouds taken by the Italian group by Milone et al. And I show 4 clusters here, 4 different star clusters, just to convince you that this is a rather universal pattern which comes out of this. So let's look at one of these clusters here, maybe NGC 1755. What you see is that the main sequence is basically split in 2 components. There is a major main sequence here, where most of the stars are located. But then there is a second main sequence on the blue side. The stars to the red side here are just visual binaries, so I don't want to discuss them here, although they're also very interesting. But we have these 2 components of the main sequence, which you see in all the clusters. There's a third component, which I do want to discuss, which is most clearly seen here in NGC 330, which is the stars marked in red. They form a third group, which extends from the turn of just 2.5 magnitudes downwards and ends here. Now, they are marked in red because they show hydrogen emission lines. So those are very likely all BE stars. So BE stars are the B stars with emission lines, which are probably rotating very rapidly. So if we look at one of these clusters in more detail, let me again stress the components I want to discuss here. So the major main sequence, which is very narrow, contains most of the stars. Then maybe 20% of the stars sitting here in the blue main sequence. Then we have the group of PE stars here, which is a bit more washed out, but which is generally on the red side of this. The community has converged on the general conclusion that this distribution of the components is due to the internal rotation of the stars. So here we have again NGC 7055, and I overlay here isochrones fitted to these main sequences. And you see the color of the isochrones is telling you what the rotation of the stars in the isochrone is compared to their critical rotation. So the dark blue is non-rotating models up to the pink here, which concerns stars which rotate with 75% of critical rotation. And so what you see is that this split main sequence, which we see here, is readily explained by having a slowly rotating component of the main sequence here, and another component which contains most of the stars, which is well fit with a rotation rate of roughly half of critical rotation. This has been found earlier by various groups, and I think that's pretty much undoubted. The third group you don't see here is closer to the turnoff of the BE stars, which of course we know are rotating rather close to critical, so close maybe 100% or so much faster than this group of major main sequence stars here. What is also interesting is that the blue main sequence, the closer to the turnoff we go, has outliers to the blue side of it, which you cannot actually explain by even slower rotation, because there's no slower rotation than 0. And so this gives an interesting clue to the formation of the stars on the blue main sequence, which I'll come back to in a minute. So what I want to conclude from all the observations I've shown you so far is that we see on the upper main sequence 3 distinct components of spins of stars, or spin rates of stars. The major component has a rotation of the order of 50% of critical rotation, which we call component A. Then there is about 20% of the stars which are BE stars or OE stars, which perhaps rotate in the range between 80 and 100% of critical rotation. And then we have a third group of stars which rotate slowly, and the exact rotation rate we cannot see from photometry, but if we go to the spectroscopic results, then this corresponds roughly to 20% of critical rotation. Now, I want to put up a bold hypothesis here, which is going to be one of the major punchlines of my talk. The hypothesis is that actually all stars are born as part of component A. That means all stars are born with about 50% of critical rotation, while component B and C are born as binary evolution effects. And I will try to, of course, give you arguments of why this hypothesis is put up. We analyze this by doing detailed binary evolution models. And in order to calculate these, nowadays we use the MESA binary stellar evolution code managed by Bill Paxton in Santa Barbara. And over the last years, what we have done is evolving a lot of binary physics, first in our own code, but then this has all been put into the MESA code by various efforts. Mostly Matteo Cantiello, Pablo Bachon have done that by supervision of Bill Paxton. And this physics includes, well, differential rotation, for example, rotational mixing is important in the massive stars. Non-conservative mass and angular momentum transfer due to Röhrschlop overflow, tidal coupling of both components, internal angular momentum transport by magnetic fields, and of course detailed nuclear reaction networks. So this is full-blown binary stellar evolution models, and MESA code allows to calculate very many of them. And so we do that, and the result of this can be seen here in this brief animation. What I show you here is the evolution of a large grid of binary evolution models in the Hertzsprung-Russell diagram, chosen in such a way that it simulates a star cluster. So all the stars which you see in the plots have the same age. And at 0 age, obviously all the stars are located just on one line, which is the 0 age main sequence. And if the evolution would just concern single stars, then this line would just change as function of time, but it would still remain one line. However, we have binary evolution here. And so what you see happening is that as the stars expand, they will start Röhrschlop overflow in some of the binaries, and we will produce many objects, many stars which are not on this single star line. And in particular, what you see is that we find a component here to the red side of the main sequence. The color coding is the rotation rate of these stars. So these red stars here are all spun up stars which accreted matter from a companion. But also we get a sequence on the other side of the main sequence, which is mostly merger products. And so if we stop this at a time corresponding maybe to the clusters we've seen, then you see we get the split main sequence. So we get the red component here, which goes 2 magnitudes or 2.5 below the turnoff. And we have the component here to the blue side of the stars, which occurs because we have stars which rejuvenate. So the merger products bring fresh hydrogen to the core of the stars, and the stars then appear to look younger. However, they have, of course, the same age as all the other stars on the picture. And so the message from this simulation is that the component B, so the stars which rotate very rapidly, we can explain as spun up stars from accretion. Now, this is not a new suggestion that this happens. Already in 1981, Puckett has proposed that 5% of mass accretion can actually spin up a star to a critical rotation. And recently in a paper with Ben Hastings, we shown that this accretion process can actually, in a population, lead to 30% of the stars being spun up BE stars. So, I'm sorry. So the idea is that the BE stars, which we see, are likely produced by mass accretion. And there is a competing single star scenario also to form BE stars. However, we see no BE plus main sequence binaries in the Milky Way, as shown by Bodensteiner in a recent paper, which means that if single stars would form BE stars, we should find such objects, but we don't. So there's a lot of evidence that the majority of BE stars are actually formed in the way I tell you here. Now, we have very rapidly rotating stars then, and this will be interesting in various respects. So these BE stars have accreted from a companion. The companion is more evolved. And in most of the BE stars, it will actually be a compact object. If it could also be that the compact object was born with a kick, and then we would have actually a runaway star. So the BE star should be a runaway star. So we should still see the impact of the explosion on the star. On the other hand, we have to notice that these BE stars still have a massive hydrogen envelope. So these BE stars will not be able to produce very rapidly rotating stellar cores, because in their post-main sequence evolution, they will become red giants, and the red giant envelope will actually slow down the internal core rotation. And so we will probably just get ordinary supernovae out of these stars. However, the companions, if they are not kicked off, they could be seen. And so what this picture shows you is our prediction for the fraction of binary stars as function of the rotation rate of the OB star, which do have black hole companions. Now what you see is this is a logarithmic scale here. The vast majority of the predicted black hole binaries in the Milky Way are expected to have very high rotation rate. Sorry. It's also interesting to look at the binary periods predicted by these evolutionary calculations for the OB plus black hole binaries. And again, what you see here is the distribution ranging from 3-day orbital periods to 1,000 days. And the peak of this period distribution you see is well beyond 100 days, which means that all these objects will not be able to produce X-rays, because for the wind accretion, this is just too wide an orbital period. However, the BE X-ray binaries, which we do see, which have neutron star companions, they have a period distribution according to the blue line, and that fits our prediction rather well. Here, by the way, is the location of MWC 656, which is the only known BE black hole binary in our galaxy, which is almost in the peak of the distribution here. So that's an X-ray quiet system. The tightest binaries, of course, they can do wind accretion and X-ray radiation. And so this dot here represents Cygnus X1. The component C, I didn't discuss much, and I don't want to spend too much time here, because for the purpose of energetic supernova explosion, they are not so exciting, because they are slowly rotating. But the idea is that this component is actually produced by binary mergers. Star formation theory is predicting that 30% of the binaries which form are merging even before hydrogen burning starts. And the merger products are expected to rotate slowly, because the merger product puffs up and emits a very strong equatorial wind in the merger phase, and that slows down the star. And this idea fits very well with the 30% of the main sequence stars are slow rotators in the B stars. Now, how do we get powerful explosions? Well, we need fast spinning cores to produce things like gamma ray bursts and superluminous supernovae. And stars which we have been discussing so far actually are all spinning, evolving slowly spinning cores. However, there is the exception of very massive, very close binaries, which can evolve chemically homogeneous. And actually, Selma de Mink, our previous speaker, has shown that in a paper in 2009. So this shows as function of mass and orbital period, the rotation rate we expect from very close binaries due to tidal coupling. And it can go to very high rotation rates, especially for the massive stars, which is much higher than the rotation rate we expect in single stars. And in our simulation, we can actually see these chemically homogeneously evolving close binaries as well, because that's the first dots here which stick out at very high mass to the left side. So these guys are the chemically homogeneously evolving binaries. It's just very, very few. And perhaps that's okay, because if you want to produce gamma ray bursts, then only one of 1,000 very massive stars should do this. Now, what we need is the chemical homogeneous evolution, and what has just been shown in a paper by Ben Hastings is that if we do this in close binaries, then the mixing inside these stars is actually faster than if we consider a rapidly rotating single star. You see this in the outcome here of the final black hole masses in these close binaries, where the green dots show you what the black dots show you what the standard mixing picture would predict. But if we use the enhanced mixing, as this has been found by Ben Hastings, we can produce chemically homogeneously evolving stars in these close binaries, also with mass ratios which are more extreme, and also with with stellar masses which go down to roughly 25 solar masses or so. Now, this is just using the very simple analytic linear theory of the adding sweet circulations in these three-dimensional distorted binary components. In reality, the mixing may be even more efficient than what we've assumed here, and perhaps allow us to populate this diagram in a wider space as well. What we learned from these enhanced mixing models which undergo chemically homogeneous evolution is that they really are very good candidates for long gamma ray bursts and superluminous supernovae of type 1a. And that you see that from a recent paper by Aguirre-Dena et al., where as function of the initial mass of these homogeneously evolving objects, what we plot here in the green and blue curves, the average specific angular momentum of the stellar remnants. And this blue curve measures it at a mass of 1.5 solar masses, and this green curve at a mass of 5 solar masses. You see triangles on these curves which estimate whether we expect actually the stars to become neutron stars or black holes. If they become neutron stars, then we should look at the lower curve here. And what we see is that the neutron stars would have of the order of 10 to the 15 square centimeter per second in terms of angular momentum, which is what we need for the magnetar model of superluminous type 1c supernovae. On the other hand, if we look at the upper curve, you see the models we expect to form black holes and collapsars in the collapsar picture of long duration gamma ray bursts. And here we get 10 to the 16 square centimeter per second, which is indeed what we need for this scenario to operate. Now the
Norbert, 5 minutes.
Thank you very much. These models include the magnetic field formation due to differential rotation proposed by Hank Sprout. And so if we look at the toroidal magnetic fields produced in these models, we find them at core collapse to be of the order of 10 to the 9, 10 to the 10 Gauss. And the prediction would be, if you assume flux conservation, that we form neutron stars in this way, if we form neutron stars, of course, which have magnetic fields of the order of 10 to the 15 and 10 to the 16 Gauss. Again, this is a good order of magnitude to explain magnetars. This is the distribution of magnetar magnetic fields, which the supernova community deduces from the observations of superluminous supernovae. So we actually have a little stronger fields here than we would need. Now, yeah, so the idea is that perhaps this relates to the fact that we use equilibrium assumption for the magnetic fields with this Power-Taylor dynamo. The timescales in the final phases of stellar evolution become so short that perhaps this way we overestimate the fields a little bit. But still, it's a possibility that the fields are in the right order of magnitude. Finally, here we see that when we use Aguirre-Denas models and predict the and derive the predicted neutron star spin and the ejector masses of these models, where we just assume a typical neutron star mass of 1.5 solar masses, that this is well in line with the observed plethora of superluminous supernova observations, which are the points in the background here. Finally, I want to say a word also on the pair instability supernovae, which Selma de Mink has just been discussing in detail. So what we get when we have these chemically homogeneous binary models, we of course also produce very massive cores, which then undergo pair instability supernovae. And what you see here is a prediction of the rate of pair instability supernovae produced by exactly this channel, by only this channel, as function of redshift for various observational limits here. So the blue line includes actually all the models which are predicted, and the various colored lines adopt a certain magnitude limit for supernova observations. And the message I want to give here is that, especially with LSST coming up, the pair instability supernovae, which are predicted from the chemical homogeneous evolution channel for the black hole merger binaries, make strong prediction also for the occurrence of pair instability supernovae. And thus the pair instability supernovae can serve as an electromagnetic test for this model. So if we believe that binaries can form double black holes this way, then they should also form pair instability supernovae, which we should observe. That's all I wanted to talk about today. So my first message is that perhaps all stars are born with the same rotation, which is very interesting because it rules out a lot of possibilities of forming rapidly rotating stellar cores. A large fraction of main sequence stars may actually originate from mergers, which is interesting to understand the magnetic fields measured in some of the main sequence stars. The most rapidly rotating main sequence stars may actually host compact objects as companions. And finally, the most energetic explosions, the gamma ray bursts and also superluminous supernovae, may come from the tightest, most massive binaries, which is a scenario which works best at low metallicity. And hereby I stop and be happy to take your questions.
Okay. Thank you so much, Norbert. There are any questions in the audience?
Yes, Norbert, thank you for this very beautiful presentation and so general and interesting. And I have first one statement from the gamma ray burst observation that we are following. Of course, not all gamma ray bursts, but a few of them harbor a black hole. But and they are the most energetic, the one over 10 to the 52 to 10 to the 54. They have a black hole, but not formed by the gravitational collapse, but by accretion of the supernova ejecta onto the a companion neutron star. Therefore, not a direct formation of the black hole. But then after this statement, I have asked you a question. One of the most important results in this MG16 has been the change in the mass of Cygnus X1 from 10 all the way up to more than 20 solar masses. Yeah. Are your simulation offering a possibility to understand simply this more massive value of the mass of Cygnus X1?
So when we do our binary evolution models, what we assume when we talk about black hole plus OB systems is that the black hole progenitor is a stripped star, so it has lost its envelope. And what we assume is then that the remaining helium core mass is actually equivalent to the black hole mass, which comes out. So all the helium-rich material falls into the black hole. If we do that, then the black hole mass distribution, which we predict, indeed reaches up to 20-25 solar masses. So it's at the end of the mass distribution for the black holes, which we predict, but Cygnus X1 still fits nicely into our suite of results. Concerning your first remark on the accretion of the black hole, which is needed for the gamma reverse, that's, I understand that's, of course, very relevant to say. The key is that, of course, in whatever scenario you produce, I think also there you would need to have an extremely rapidly rotating core.
Yes, absolutely.
So I think in that respect, the models which I discussed here also, are relevant for this.
Absolutely. And you will hear some presentation later on this morning. Thanks
okay,
again.
Are there more questions?
Yes, Massimo?
Yeah.
Can I formulate my question?
Yes, of course.
Okay.
Go ahead, please.
Thank you, Norbert, for this very insightful presentation. My question goes through the last 2 points of your summary, because that is the most interesting part for us working on the binary models of gamma ray burst. So if I understand correctly, you look into the evolution up to the point of the supernova, but still the two stars were in the chemical evolution. So after the first supernova, in fact, as you say, one of these systems can make them host a compact star. But have you looked into the further evolution of these systems?
No, not in these models. Sorry. Yeah, I should have made that clear. No, we didn't. There is certainly further possibilities in binary evolution to produce, say, also very much rotating stars, which have some different origin. And in that context, for example, the predictions from the chemical homogeneously evolving binaries, which I showed, they work really best at low metallicity, but of course we know that there's, for example, also some gamma ray bursts at high metallicity. For those, our models do not really offer a solution. So there will be still some additional channels, which have been also proposed, in the literature in the last years, for example, by Remo and others, which will need to explain the high metallicity events. So they are not coming out from the channel I discussed here, but I think they are also not the majority. So the majority of events is still covered by what I said.
So just to clarify, I was speaking about the system in which you have still one of the stars and you have a host, you have a companion, which is a compact star, for example, a neutron star. And so the neutron star, this binary system continue to evolve, and the neutron star will affect the evolution of the other stars. So this is my question was pointing to those systems.
Yeah, so this phase is not covered by the models which I showed.
Okay, sorry, Norbert, I have a question myself, very short. May we conclude that a significant fraction of the progenitors of core collapse supernovae are hosted in massive binary systems? I mean, core collapse, I mean type 2, 1b, 1c, broad lines, and so on.
Well, so the observations of massive stars show that almost all massive stars are part of binary systems. Now, during binary evolution, that's a part I did briefly discuss only, there's a lot of stars which merge as well, maybe 30% or so, maybe 50%. These merger products then are predominantly single stars. Yeah, so when they evolve to supernovae, they don't have a binary companion. However, yes, from the rest, we would expect that in most circumstances, we have a binary companion present at the time of the supernova. So it's a rather the rule than the exception to expect this.
Okay, thank you so much. We can move to the next speaker, Jiri Bikek, and going to talk about the dragging of inertial frames by matter and waves.
Okay, well, thank you for introduction. Thank you for giving us possibility to talk, me and my colleague, Tomasz Ledwinka, who will tell you something about dragging by gravitational waves. But I would like also to thank organizers for enabling our colleague, Oldřich Semerak, to organize session on dragging. And I shall quite often quote from this section, and it would be nice if materials from the sections would be also available to everybody. So it will be more theoretical talk, although I will speak also about experiments, and I will start more historically. So let me first start in the following way. Imagine that we are now, I assume that in San Francisco, we have now night, and so hopefully there is a starry night. Imagine that you run away on your garden in San Francisco and you start from pleasure just to rotate. And you look upwards and you see rotating stars, but simultaneously you see that your hands go up because you appear in an inertial frame. And of course, non-inertial frame because the stars, the distant mass is rotating with respect to you. This is a typically Machian point of view, and I will speak about Mach principle, which is quite inspirative, I think, until today. But let me first be a little bit historical or perhaps even patriotical, because here you see map of Czech Republic with a number of actually Czech Republic and former Czechoslovakia. So Ernst Mach spent almost 30 years in Prague and certainly influenced enormously Czech physics. Here he wrote the Science of Mechanics, which were so influential. And I think it was thanks to the influence of Ernst Mach that also Albert Einstein was spending 1.5 years in Prague and was invited from 1911 till 1912. And make actually quite significant contributions and progress towards general relativity. I shall omit the other people which I have here. Let me just quote one thing from Mach, namely from his Science of Mechanics, that the investigator must feel the need of knowledge of the immediate connection, say, of the masses of the universe. There will hover before him as an ideal insight into the principles of the whole matter, from which accelerated and inertial motions will result in the same way. So I should first say that we organized actually on the occasion of 150th anniversary of the birth of Ernst Mach conference. It was in Prague in 1988. So these were still dark ages, but we could invite some quite important people like Jürgen Ehlers, and who came also was Julian Barber and Herbert Pfister, both enormously interested in Mach and Machian general relativity. And in fact, here in Prague, they agreed that they will organize a conference in Tübingen, which they did then later in 1993. And there is a beautiful book, I'm not exaggerating now, which is on Mach's principle. And it includes also a lot of discussions in the text. I mean, the editors very carefully prepared this book. And so there are people like Hoyle and all these golden oldies, Rindler, and of course Barber and other people, and it's quite worthwhile to look at these discussions. The first paper, and that is why I started historically on dragging, actually comes really from Einstein. And we have heard in the section, actually, and in other lectures, how Einstein was important also for discovery and the description of land steering effects. But the first paper was in Prague, written by Einstein, and it is in English is a gravitational effect, which is analogous to electromagnetic induction. He considered on the basis of his Prague version of his gravity theory, which I will now not do details about, but it successfully went to eventually general relativity. So he considered a spherical shell of mass, and mass is the center. And when he started to accelerate this shell, so of course in Newton's theory, you would have no effect inside. But here, you must keep the mass point. The mass point is dragged into acceleration together with this shell. So this was the first symptom of dragging, not with rotation, but with this dragging, linear dragging, one could say. Now, this is the session to which I will refer several times. It was on Monday, actually. You see that it also has a joke, Mach, in the description. It's the dragging is never draggy, mass and charge flows in GR. And all these lectures were extremely interesting, and some of them will describe in more detail. Not all were concerned with Machian effects, but still, I mean, for example, this was typically relativistic talk by Philip Costa, who considered gravitomagnetism in cylindrical spacetimes and very pedagogically distinguished rotating cylinders from stationary cylinders. There is a lot of mass in these understanding of these true infinite systems. But I shall mention Vladimir Kara's talk and Blandford talk and Van Son talk because they were more closely related to what I want to speak about. Now, according to Machian point of view, of course, if you have Foucault pendulum, say, on the pole, it should be on the south pole because there is really laboratory. And you have starry night, and the Foucault pendulum starts to oscillate. So these fixed stars keep the plane of the Foucault pendulum just in this vertical position. However, we have also Earth, which is rotating. And so this mass, although very by small effect as comparison with all mass in the universe, will also turn the plane of oscillation of this Foucault pendulum. And there is an experiment which was suggested, unfortunately not realized, because apparently it would bring a lot of possible measurement errors, by Braginski, Polnareff, and Thon, Foucault pendulum at the South Pole. And it's a proposal for experiment to detect Earth's general relativistic gravitomagnetic field. It was in the time when already gravity probe B was under plan, but still these authors, the paper is quite interesting and contains a lot of estimates of possible errors. Of course, this gravomagnetism is completely analogous to electromagnetism. The following effect: if you have a charged sphere which is rotating, it creates magnetic field. Similarly, if you have mass which is rotating, it creates what is called gravomagnetic field. Now, the main experiment, I should say very controversial experiment on measuring this dragging was gravity probe B. It lasted almost half a century from the first idea to realization. And unfortunately, there were some errors like random patches of electric charges on the rotor. The rotors were actually 4 gyros, which were here in the satellite. And there was a guiding star which determines the direction, and one could determine how the axes are changing. I will not go in detail describing this experiment. Unfortunately, the error was quite big of this frame dragging, but still the result agreed with GR prediction. Yesterday we had nice lecture by Professor Ignazio Ciufolini, who considered another experimental confirmation of dragging of inertial frames NI by dragging of nodal rays of 3 laser-ranged satellites. And I shall just refer to this or to the book also by Ciufolini and Wheeler. Now, let me go to the following fact, namely to dragging of magnetic fields by rotation. And this is the picture first, very astrophysical. This is the nucleus of galaxy M87, where we know now that there are a black hole which has several billions of solar masses, perhaps even some estimates are 7 billions. And there is enormous jet which goes to 5,000 light years away from the center. And general wisdom is that this jet is caused by, as it is written here, introduction of frame dragging around black holes, rotating black hole with magnetic fields. And this is responsible for production and generations of jets. Now, about this M87, there was quite long contribution by Roger Blanford at this session organized by Oldřich Semerák. And I wrote him, he sent me actually the slides, and this is his summary, which is in some respects surprising. It first says that Event Horizon Telescope observations of M87 provide magnificent affirmation of black hole model of AGN. There is no doubt about this. But there are two interpretations. One is interpretation of the jets that, and of the whole system, that its standard is that we observe a thick pressure-supported accretion disk. But there is alternative that actually all energy or most of energy supporting the jets comes from a magnetosphere around a spinning black hole that expelled almost all accreting gas and confines also the jets. There are, and Blanford, although he's the main protagonist of this magnetic extraction by this Blanford's neck mechanism. So he admits still it's not completely conclusive, but he says that it ought to be possible to distinguish these two interpretations observationally. And of course, jets are in many astrophysical systems. So, you know, it's even in stars which are just being born, etc. So this is very important theoretical issue, and there are now very big computer simulations of these things. Let me still be a little bit historical. I was enormously enjoying Marcel Grossman meeting in Paris in Australia in 1988. I primarily was talking on radiative space-times, more mathematical relativity, but in Carter section, I spoke about our work with Vladimir Karas on dragging of magnetic field lines around rotating black holes. So you see, these are field lines which are aligned along the axis of symmetry. And here is clearly seen this effect if the black hole becomes extreme. So these magnetic field lines are expelled out, and it's so-called Meissner effect or black hole Meissner effect. And whereas here is the field which is perpendicular to the axis of symmetry, to rotation axis, and this is very much dragged by the black hole. It depends, of course, in what type of coordinates you draw these field lines. So this is in with respect to ZAMOS, the zero angular momentum observers, and this with respect to observers which are falling in. But in both cases, one observes, and this is what Vladimir noticed and elaborated in many papers until today, the 2 points at which the magnetic field becomes zero. So in principle, there would be plasma. So one could have here magnetic field lines reconnections. Here, these pictures are actually for vacuum magnetic fields. Now, you see, this is just this example of Meissner effects. Here, these figures, you have current loop around rotating black hole. So this is a general black hole, which has the rotational parameter about 0.9 of mass. And there is some expulsion, but there are some field lines which go in. Whereas if you have a maximally rotating black hole, you get all expulsion. So this is still better seen in maximally charged Reissner-Nordström. In principle, it is interesting. We don't believe that we have maximally charged Reissner-Nordström in the universe, but you see how beautifully if this is dipole. So you have here magnetic dipole, which is placed above this maximally charged black hole, non-rotating now. And you see that here there is no influence on these field lines. However, if you approach very closely with this dipole, so you see that all these magnetic field lines will be expelled. And so this is described in this paper and then followed in many others, but it's interesting that this Meissner effect actually appears also in various supergravity theories and in string theories, which as it is demonstrated here in this paper by Gibbons, Emparan, and Chablin. Now, these are still pictures of magnetic fields, which is perpendicular to the axis of rotation. Here is indicated which field lines enter, here is indicated which field lines go away. You see there is no flux expulsion even from extreme black holes if the field is not axisymmetric. All these Meissner effects were for the field which is axisymmetric, and here is calculated directly how the flux of magnetic field looks like if the hole becomes extreme, because then the flux goes to zero, but it is non-zero even for extreme black holes, and then its calculation what should be actually inclination of this hemisphere with respect to the axis of magnetic fields, which have here and here the components along the axis and perpendicular to the axis. Now, these are nice pictures by Láďa Karas, and there is this citation of dragging of these field lines around rotating black holes. And the color indicates the intensity of the field. And here you see there is a point, this is this null point, where, or a critical point where the field vanishes. Now, Karas and his collaborators continued with exploration quite a number of years of these various magnetic type of fields around black holes. And I selected here just one of the last paper, and in fact, a more detailed paper is in Astrophysical Journal, also from the last year. And this, these pictures show how the, how if you take Novikov-Thorne thin accretion disk and particles go inside the rotating, this is non-rotating black hole, but here it is rotating. So what can happen is that neutral particle close to the black hole get ionized. And if you have magnetic fields then, magnetic fields again, which has component which is perpendicular to the axis of symmetry. So you can find there is a number of particles, and these are these yellow in these figures, which can be ejected and accelerated away from the disk. And actually this is what could in principle form the funnel or the jet which goes from such sources like M87. So actually more details, but everything is quoted in this paper, is in this Astrophysical Journal paper. Now, let me go to the more pedagogical, but still interesting, because very recently we considered this effect, or primarily Van Song considered in Perimeter Institute and others, in quantum regime, which is, I think, first time when it was demonstrated that dragging of inertial frames can be detected by quantum wave. I hope still to have time and describe this later. But this is a classical example which started with Lindblom and Brill, considered rotating, slowly rotating, but also collapsing shell of matter. And you can arrange the thing so that you take care, slowly rotating care outside, and you join it to flat space still inside. But you find out that actually local inertial frames get into rotation with respect to infinity, with respect to fixed phi at infinity. We did a very detailed paper here with Joseph Katz and Donald Lindenbell in '98, but then there is much more detailed and with animations, I can show you in this paper with Tomáš Ledvinka and with Will Barker on the same effect in classical quantum gravity. We considered already with Joseph Katz and with Donald Lindbell how actually stars look if we are in this rotating, inside this rotating shell. And here you have just explanation how you can join
the metric inside and outside, and you see how these local inertial frame get into rotation. So this is just animation which can be found in classical and quantum gravity of collapse of slowly rotating shell, but it's not collapsing completely. It's actually, again, it's actually oscillating in principle, because you can do counter-rotating orbits, so that now the shell bounces and goes out, and the gyroscope is changing its direction because of dragging. So I will now ask Tomasz, and he will tell you something about dragging by gravitational waves.
So hello, there is quite a long history of using scalar wave solution to scalar wave equation to generate exact or approximate gravitational waves. One of the most well-known is the classical Weber-Wheeler-Bonner pulse in a cylindrical symmetry. So there is something like center axis towards which the gravitational wave converge, and then they again back towards the infinity. And this was somehow improved or extended to have also the angular momentum. So now there is available in this paper solution, exact solution, which admits strong gravitational field generated by scalar function, which is now in this animation. And sorry, let me try it again. So you see that the waves converge somehow towards, and so that they have the angular momentum, they are separated into these angular peaks. And the trick is that once you have this solution of scalar wave equation on flat background, you can upgrade it to this strong gravitational waves. The same or very similar approach can be used to get linearized gravitational waves, which now form spherical shell. And it is interesting because in this moment, it is very Machian experiment. You have a shell of gravitational waves, which is here plotted in this red strip in the compactified Minkowski space-time background. Then you have observer, which is in the center. And in this, because the gravitational wave, as you saw in this animation, somehow are vanishing in the center, you have flat space in the first approximation in the center. And there is big difference in between the let's say land steering effect of massive shell, which trajectory hits these future and past infinities, while here the gravitational wave hits null infinities, these cries. So there is one difference. The other one is that if you have this limited pulse of gravitational waves, in past history there is completely flat Minkowski region. And to make it Machian, you can also have now not massive, but some kind of test stars which emit optical radiation, and you observe this radiation in the center. So now you can compare your experience, which is somehow oriented by your local gyroscopes, with observation of stars distant. And these stars are, the light from these stars comes in this compactified diagram along these 45 degrees incoming geodesics. Now, what is interesting is that you can use the perturbation approach, and this H1 is the gravitational wave, which is chosen to be generated by this scalar wave you saw in the animation. Here is the prescription that you have this psi solution of the flat wave equation, and then you generate this psi1. Of course, as it is made, this H1 carries angular momentum, and it also vanishes in the center. So if you write down the perturbation equation for second order perturbation, and if you consider or discuss the meaning of the gauge, then you can find that it is well defined, the rotation in the center. You can also imagine it that you use this high frequency approach to gravitational waves, and as a result, you somehow can get the perturbation in the center decomposed into spherical harmonic or tensorial harmonic, and that one with L equal 1, M equals 0 is the one which describes a center rotation of the frame. And it is this equation which you get by projecting Einstein equations. And at the end, if you solve this differential equation, you get the angular momentum of the rotation of the center frame in this form of this integral. There are two interesting things on this integral. First one is that this RT phi is in fact the same quantity which appears if you study the effective angular momentum of the gravitational waves. But of course, if you want to get this angular momentum, you have to integrate it by the volume element, which is r squared d omega dr. So what you get here is, if you consider this omega 0 is different power of r, which means that you get at the end, if you consider thin shell of gravitational radiation, you get a discrepancy of r cubed. So it means that there is proportionality between the angular momentum of gravitational waves and the observed angular momentum of rotation by power of 3. So, and the other interesting thing is that because of the chosen heritage of the Weber-Wheeler pulse, you can integrate these things analytically and you can get exact formula. But as I mentioned, there is light coming from the distant stars and you can observe them, and you can also integrate these perturbed geodesics and observe the light trajectory on your sky. And the interesting thing is that you will first see this large wiggling of the star on your sky, and it is due to the first order perturbations. So you see some trajectory, but also you can see the shift between the initial star position and the end position. And it is due to the fact that during your world line, you are rotating with respect to infinity. And this discrepancy is the integral of this quantity omega you get here. So even if there are some problems with fixing gauge, this is gauge invariant quantity you can really observe by seeing stars. In fact, you can also observe stars all around your sky, and you will see pattern of this wiggling of stars, which will relate to the function, to the wave solution you have used for your seed solution. So let me switch back to Yichi.
Okay, so just we have a couple of minutes, I hope. So let me first say a few things about something which was done with perimeter people. The primary creator was actually Van Zong, who spoke about these things in session PT5 of Semirak. And what was considered is Unruh de Witt detector, which is two-level quantum mechanical system. And this detector is interacting locally with scale field. And what we considered is what I mentioned before, that was a slowly rotating shell. Now it is not collapsing. What one starts is that one takes the system in ground states and interacts this detector with vacuum via the interaction. This is interaction Hamiltonian, where there is coupling, there is monopole moment of detector, and this is the scalar field. And what Van did is a detailed numerical study of something what is called the response function of the detector. And it really does differ for the detector which is placed respectively in a rotating shell or a static shell. So this is just mathematics for which we now don't have much time, so that one should look at the papers or one's contribution. And this response function, however, is here numerically evaluated and graphically illustrated. So you see that this response function, this is the difference between a response function of rotating and static shell. And if the shell is rotating, so as rotation parameter increases, so this response function becomes different from static case. Also, this response depends on where you locate your detector. The far away and closer to the shell, the detector is more influenced by this rotation. And also the detector at the axis is not, but if it is away from the axis, so it is. And what one should emphasize here is that this effect is such that it's this observation time, or as it was here, this switching function, which is here. So the switching function is chosen so that it is shorter than the light needs to go from detector to the shell and again back in classical way. So this quantum effect actually indicates that these things can be detected much quicker. Let me remind you, this is an interesting, also very distant sentence in Abraham Pay's beautiful book about Einstein. There is statement that still there is something important in Mach's ideas and Mach's principle, but that one should do it quantum. So it starts with quantum, and of course it's far away from Mach. Last point which I would like to mention was our detailed analysis with Donald Lindenbell and with Joseph Kass of Mach's principle really in cosmological settings. And it was also inspirative for formulating various conservation laws. And what we took is Bondi's formulation, old formulation of Mach's principle, but we really have shown that in a linear perturbation theory, it is satisfied. And it says that all motions, velocities, rotation, accelerations are relative, and local inertial frames, and that was our main goal, are determined through distributions of energy and momentum in the universe by some weighted averages of the apparent motions. And this is illustrated in this very long paper in Physical Review. And what we consider, what I think is useful regardless of Mach's principle here, is that we found some gauges which we called Machian gauges, which are actually very close, this is just quotation, which are very much more unique than, for example, synchronous gauge and comoving gauges which are used in cosmology. And what is their role? Let me show here on the equations. The point is that all these dragging effects are actually something which comes from, that was the same with gravitational waves, from the constraint equations. So it is something which propagates instantaneously. So you want to find such gauges in cosmology, in linear perturbation theory, that you get as many elliptical equations as possible. So you take the gauge in which mean external curvature perturbation is zero, in which something which is called minimal shift conditions, which is equal to zero, and then you can really solve this problem nicely. What I missed and what I didn't say, but just very quickly went over, is that actually this Mach's principle considerations, and actually perturbation theory in cosmology, inspired us with Lindenbell and Katz to formulate something what today people call KBL superpotential, and it's a superpotential which enables one to calculate energy so that you choose backgrounds, and the background will have zero energy, and you do just the energy for perturbations, and they can be even large. If it is linear, it is just here, this difference, and all this is in these papers here. So I believe that Mach's principle could be still inspirative, and so I finish here with this Rembrandt engraving of apparently Faust. Thanks.
Thank you so much for your talk. I particularly enjoyed this relay race talk, by the way. We are a few minutes late, so I will take one question.
I think this talk has been so important that I have at least to make one statement. It's fantastic to have seen this reconstruction from one of the first Grossman meeting, which went on in the Italo-Korean meeting later on. This beautiful work Giri made about the magnetic field around a black hole, a Schwarzschild black hole, a Kerr black hole, and especially with the charged black hole. We have seen the evolution, remarkable, beautiful evolution in the work of Karras. If I have to say one word, the novelty Giri, with respect to this historical development, has been the new concept which we introduced very, very recently about the effective charge. Charge are not present in care solution with the magnetic field, but there is a concept of an effective charge which comes from the coupling of the gravitomagnetic field of the care plus a background magnetic field, and this is the effective charge which is present also in the wall solution, which is the heart of the acceleration in active galactic nuclei and GRB. You will hear maybe a short presentation later, but let me congratulate about this. And since one of the key volumes published on this topic was in the Italo-Korean meeting, which we had long ago, I would like to take the occasion of this presentation to let know that in the month of August, there will be a meeting, a Italo-Korean meeting, and I hope that you will present there a review of all this work, and we will also join with the effective charge concept. And coming back to the beautiful presentation of Ledvinka, nobody could be happier and really a celebration to see finally an image of the Geon. John Wheeler will have liked incredibly to see this representation of Ledvinka. I don't know if this was Weber and so forth. I know for certain that that was the idea of John Wheeler about the electromagnetic Geon and gravitational wave. And I even gave a lecture at the first meeting, one of the first meetings in the PS about this image. But now we have seen really reconstructed by Ledvinka. Congratulations again.
Okay, thanks for your remarks.
Okay, thank you so much, Giri. And let's move to the next speaker, Ivan Dimitri, that is going to talk about observation of high energy cosmic rays.
Okay, good morning. Can you hear me?
Good morning, yes.
So good morning, good afternoon, and good evening, actually, to everybody, since because of the time zone. And thanks so much to the organizer for the kind invitation. I'm trying to go to full screen. Okay, now will be okay. So I was asked to give a review talk on recent advances on the observations on high energy cosmic rays. Of course, as all review talks, this is a difficult task in order to try to take into account all the latest development in the field. So I will cover only partly, because it's impossible to cover all interesting things in a single talk. In particular, I will concentrate on some key aspects of cosmic rays observations above few GeV up to the highest energies, namely 10 to 20 electron volts, so more than 10 orders of magnitude. So this implies very different experimental techniques and very different problems in the observations and solutions and so on. I used many slides from almost the whole community covering this energy range, and in particular, I would like to thank all the speakers of the parallel session. Sorry for the typo, parallel session HE6, which covered the observation of high energy and ultra energy cosmic rays. So I invite you, if you want to have a closer look to this stuff, to have a look to their slides on the Indico page of the conference. So let's start. If you go back, I would say 30 years ago, approximately, you will find a picture which was maybe oversimplified, but the most present plot that you would find on lecture notes or whatever is the upper left. So the energy spectrum of cosmic rays, summing up all the cosmic ray components, the so-called all-particle spectrum, as a function of energy, could be approximated as a power law with a spectral index which is not actually constant. It was 2.7 up to a certain energy, around 10 to 15, 10 to 16 electron volt. This change of slope was called, and is actually called currently, the knee, or the energy spectrum. And then a continuation again as a straight line, so a power law with a spectral index of order 3. Then another feature with a hardening, it was called the ankle. And then we didn't know what happened around 10 to 20 electron volts, even if we expected to find the famous Greisen-Zeppelin-Kutzmin cutoff because of the interaction of cosmic rays with the cosmic microwave background. We didn't know actually which were the sources of cosmic rays. The hypothesis, the explanation, I would say, of this flux is given here on the right. The most common explanation was that we have galactic sources, maybe supernova remnants, accelerating protons, and then helium nuclei, and then iron up to a given energy. Reaching a maximum energy, which is then explaining the structure of the knee. And then there was the hypothesis of another population of galactic sources covering the energy spectrum up to the highest energies, where then the extragalactic sources might be even more important, most probably the contribution of active galactic nuclei. All this, since we are talking about charged particles, should be completely anisotropic. In particular, there were some measurements showing little deviation on the isotropy, showing a dipole anisotropy with an amplitude which was energy dependent and showing a funny shape pretty similar to the energy spectrum, just by chance, I would say. So this was the picture, and it was dominated by this upper left plot showing the energy spectrum as a single power law with tiny structure around the knee. So now we know this is mostly updated plot to the last International Cosmic Ray Conference. We know that this is not really true, because you can see in this plot again the energy spectrum of the old particle flux multiplied by a power of the energy, E2.7. So if you see a flat horizontal behavior, this means here that you have a power law with a spectral index minus 2.7. But you see that you don't have a single power law, and you don't have either 2 power laws or 3, because you have many little structures. So we see still the knee at around 10 to 15, 10 to 16 electron volts, but we see maybe another structure which was called the second knee. So this gives you the idea of the surprises that we're finding somehow. We confirm the so-called ankle around 10 to 18, 10 to 19 electron volt. And then this is really astonishing, and one of the most important results in the latest years. We clearly see a suppression of the flux around 10 to 20 electron volt. If this is due to the classical GCK effect, or if this is due to the reach of the maximum energy available at cosmic ray accelerator, this is still under debate, is still to be understood. From this plot, you also see that you have many systematic effects that make the spectrum measured by different experiments do not overlap exactly. So you have huge systematic, well, not huge, but relatively large systematic uncertainties on the absolute fluxes. But you have to take into account that these measurements were taken by ground-based array. And in this case, you have you don't have a problem of statistics unless you're working at the very high energy in the very energy range, but you have problems of systematics due to the fact that you have to assume a given hadronic interaction model to explain your data, starting from secondary particles measured at ground and willing to understand what happened at the top of the atmosphere in the first interaction. So this is something more or less unavoidable with this technique. Anyway, this is the landscape that we are going through. I always use this upper right plot. This is very old, actually. This is but it is really astonishing. This is the so-called ground unified photon spectrum, as it was called in the 80s. But anyway, you can see here the flux of photons at different wavelengths of energies. You can clearly see the bump of the cosmic microwave background here, and then you have all the thermal spectra we'll see, and then you start having power loss or non-thermal phenomena giving rise to the photon production, mostly related to the same sites where also cosmic rays are accelerated. You can see here the cosmic ray flux with these white palettes. On the lower right corner, you see the flux of the neutrinos with the holy grail of the cosmological neutrino background that it's very easy, very difficult to be detected. And okay, this will be a long story, I guess. So then you have around the MEV, the solar neutrinos, the neutrinos from supernova burst, or even reactor antineutrinos, so artificial neutrinos. Then you have the neutrinos produced in the atmosphere because of cosmic ray interaction with the atmosphere, so the so-called atmospheric neutrinos with the green curve. And then you can observe astrophysical neutrinos only going at the highest energies. So you expect to have neutrinos from AGN or cosmogenic neutrinos above 10 to 14, 10 to 15 electron volt, I would say. But coming back to the left, so the charged particle, you see here a collection of the results. Again, the old particle spectrum here. And then at low energies, you see that we can distinguish several components. The reason is that at low energies, the flux is high enough in order to have a significant number of events using a reasonable sized detector flying in space. So if you build a detector and send it in space, the acceptance that you might expect is of the order of a maximum of 1 square meter steradian, I would say. And given the flux of cosmic rays, this is setting a high energy limit that you can reach with your statistics. So below this limit, which is currently around 100 TeV, so below 100 TeV, you can distinguish several kind of interactions, because with space-based detectors, this is relatively easy. While above this limit, you cannot distinguish the identity of the primary particle that hit the atmosphere and produce the secondary particles that you're going to measure. And then you simply sum up all the species and detect the whole particle spectrum. Of course, you can do something more, even with indirect measurements with ground-based detectors, but it is difficult, and I will show you some results also for this. So this is a different version of the same picture where it is emphasized that at low energies, I would say below few GeV, the spectra are very much dependent on the solar activities. You have a cutoff due to the solar magnetic field, and you have also a variation, a modulation of the flux due to the solar activity. While above, I would say 10 GeV, these effects are negligible, and then you are dealing with most probably galactic cosmic ray sources. While at the highest energies, most probably I would say above 10 to the 17, 10 to 18 electron volt, the spectrum might be dominated by extragalactic sources. And this is just to oversimplify the picture in order to give you an idea on what we are going to talk about. So in principle, this is the electronic component. So if you measure electrons and positons and you sum up them together, you have this clear picture. This looks very beautiful. We see many experiments that agree each other, actually, but this is essentially a trick because you see on the y-axis the flux, which is represented here, covering many orders of magnitude. So this is not the way we typically represent our flux. So we typically put on the y-axis the flux times a power of the energy, because otherwise you would see that everything is mostly a power law with no structures and a nice agreement among the experiment. But this is not really the case. So typically we have the same plot here in the upper left corner. So we have the same flux as before, but multiplied by the cube of the energy. So in this way, you can see clearly the structures of the flux. You can clearly see the differences among the experiments and the systematics that should be understood. And you also see very well the variation of the slopes of the flux. Again, in particular, below 10 GeV, the flux is suppressed because of the solar magnetic field. So if you concentrate your analysis above 10 GeV, you see that there is an almost power law. Of course, there are differences among experiments, but these are within the systematic uncertainties that are quoted in each single work. And maybe there is one experiment, there wasn't one experiment. This is the picture, let's say, up to 4 years ago. There was one experiment, a ground-based experiment, actually designed for gamma ray astronomy, the S experiment, but also the Veritas experiment, suggesting a sort of cutoff in the energy spectrum of electrons and positrons around 1 TeV. This is something that is somehow expected due to the energy losses of those particles due to Bermstrahlung, for example. Then you see some dashed lines here that are suggesting that in the framework of some specific models, you might expect the presence of nearby electron and positron sources. So you might expect a rise again in the flux. And this is very interesting to be now investigated and understood. All this is difficult from the experimental point of view because you see here, for example, on the right, which is the ratio of, for example, here, of the sum of electrons and positrons with respect to proton. And you see that this ratio is energy dependent and is around, I would say, 10 to minus 3 at the highest energies at 1 TeV, for example. So this means that your signal, the electrons and the positron, has to be found in a huge background, at least 3 orders of magnitude larger. So you might have several problems to be solved from the experimental point of view. Of course, I don't have time to go through all of this, but this is just to give you the idea. The recent picture in the so-called all-electron spectrum, so electrons plus positrons, the recent result is this one. This is the result which was produced by the DAMP experiment, which is a satellite flying since 2015 in a low Earth orbit. And you can see here the flux, which was clearly measured as a function of energy. Again, the flux here is multiplied by a cube of the energy. And you see a clear break around 1 TeV. This was the first time that we had a clear measurement with dark measurements of this effect. Then you can see a collection of measurements on the right here. In red, you have dump points. Of course, there are some issues with the systematic uncertainties on the energy scale of different experiments, but remember that these are tiny effects since we are multiplying the flux by a cube of the energy. Anyway, the main message is that there is this break, and we should try to understand what will happen here at few TeV of energies. Here, the statistics is not sufficient. Dump is too small to see an eventual raise, a possible raise of the flux because of the nearby source contribution, but it will be most probably the goal and within the reach of the next generation space-based experiment. I think we can skip this because it is a discussion on the systematics on this measurement itself. Well, even more interesting is the measurements of the positron component only, because if you measure dark matter, you might produce positrons in cosmic rays for two reasons essentially. One possibility is a so-called standard. One is to produce positrons and antimatter in general as a result of secondary interactions of the cosmic ray beam propagating into the through the interstellar matter. So you have a given fraction of antimatter and, for example, of positrons that you can calculate. And in the lower left, you find one of the calculations. This is a relatively old picture, but this is not by chance that I use this one. The black line was a calculation on all the positron fraction as a function of energy. And you also can see here old measurements with very large uncertainties till the publication of the results by the Pamela experiment with the red points that showed that this fraction is rising, and this was not understood, and yet is not completely understood within the standard production mechanism of secondary antimatter during the propagation of the cosmic ray beam in the galaxy. The other reason why you might have positron in cosmic rays is that you might have dark matter candidates that annihilates or decays, and in this case you expect to have matter and antimatter. So a fraction of the antimatter that you could find in cosmic rays might come from those particles. So the study of the antimatter in cosmic rays might give you indirect signature of the presence of dark matter. This is why these results was so interesting when it was published. Then the results by Pamela were confirmed by a very beautiful measurement by the AMS detector. You can see the result as the red points in this lower right plot. And also by the Fermi satellite that does not host a magnetic field on board, but use the geomagnetic field to separate the electron and positron components in a relatively very nice way, even though their systematic uncertainty was very large. But also in this case, they confirm an increase with the energy of the positron fraction. Now, with the AMS results, we can clearly see from this plot the behavior with respect to energy of the electrons in blue and the positrons in red. The scale is not the same because the positron component is much lower. You can see a difference within the red and the blue scale. But the idea is that the behavior with energy is different. So we see that there is a positron excess clearly, and then maybe we have some approaching 1 TeV energy. We have the break that was already observed in the sum of the two components, electrons and positrons. Then you expect also an excess in the anti-proton signal, but this is not the case, and this is a puzzle which is still there, I would say, because you see here the ratio of the flux or the ratio with respect to protons of anti-protons in cosmic rays, and you see that the experimental points are well within the predictions of the anti-proton fraction without using any hypothesis on the presence of dark matter. In particular, you see in the lower plot the fraction of antiproton with respect to protons, the experimental points, and different models with different uncertainties due to cross-section calculation, the propagation effects, the modulation from the sun, and so on. You see that there is maybe some discrepancy at the highest energies, but still we are at the limit. I will not say that we have a clear excess of antiproton. And this is something that could be understood. So we have a positron excess, but we do not have an antiproton excess. I think I can skip this. So if we go back now to the standard, let's say, component of cosmic rays, so proton, helium, and other nuclei, we expect to have, in a relatively simple picture, a single power law behavior. So again, starting from the upper left, you see here a plot of the proton and helium fluxes multiplied by a power of the energy. So at low energy, again, you expect this suppression because of the sun activities, then you expect a straight line, which means that you have a single power law with a given spectral index. So first the CREAM experiments, and then directly Pamela and then IMS showed that you actually have a change in the spectral indexes, both for proton and helium at high energies. You can see the clear picture here after the beautiful AMS result. In particular, you see the proton spectrum here and the helium spectrum here. In both cases, again, apart from the separation at low energies, in both cases, you see a deviation from a single power law, and in particular, you see a hardening at few GeV of energy. This was an unexpected result, and somehow a surprise that SEAL is waiting for an explanation from the theoretical point of view. There were many papers, but many possibilities might explain this result, but we didn't identify yet a single model or a single explanation for this effect. So the question is now, what is happening at even higher energies? Or for other nuclei. This is, for example, the same result, the same kind of measurements made by MS, but also concerning other nuclei. So you see again proton and helium, but also see here lithium and then oxygen, carbon, and nitrogen. In all the cases, you see that at a given energy, in particular in this case, you have the fluxes as a function of the rigidity, so the energy, so the momentum divided by the electric charge. So at the same rigidity, which is of the order of 300 gigavolt, so 300 GeV for a proton, you find a hardening in all the cases. So this is a common feature, and most probably this should be due to acceleration, but the contribution from propagation effects is not excluded. What happened at even higher energies? So this is the proton flux as measured by the CALET experiment, which is currently running on the International Space Station, and you see again a confirmation of the hardening of the flux around a few hundred GeV of energy. And then here the measurement of CALET stops, and you see all the measurements here with very large error bars. So we don't know what's happening at the highest energies. I would say above 10 TeV. Now we know, since a couple of years, Dampe published these results on protons, and you clearly see here a confirmation of the hardening even within the systematic uncertainties, which are represented by the the dashed area. But you clearly see also a softening of the spectrum. So again, there is another change of the spectral index around 10 TeV. So we don't know if these are two independent effects, or if you have a straight line, so a single power law, and on top of this, we are observing a bump due to some nearby sources or some other effect. This is still to be understood, and actually this is the subject of investigation from our theory colleagues. Recently, so on May 18, we from Dampe published also the spectrum of helium, and also in the case of helium, you can clearly see that there is this softening at the same energy, more or less 10 TeV for singly charged particle. And well, of course, the systematic uncertainties are not that small, but if you compare the evidence of the softening for protons, which is at about 14 TeV, with the evidence of the softening for helium, which is at about 34 TeV, you might see that maybe maybe this is a factor 2 within the systematics, within the uncertainties, and this is suggesting that this effect is depending from the electric charge of the particle. So this might be a rigidity dependent effect as the hardening. So the hardening at 300 gigavolt and the softening at about 10 teravolt. Yes?
5 minutes.
Yeah, I'll try to stay in 5 minutes. If you go to other nuclei, This is just one example, the measurement of the iron flux by AMS and CALET. You see AMS in pink and CALET in red in this recent plot published by the CALET collaboration. You see that there are some effects to be understood from the observational point of view, but we also see that the energy reach is not that high enough in order to investigate here the softening region. So you need another mission to do this. I can skip this one and also this one. So the next mission that might be interesting to cover all this region, so reaching, approaching, I would say, and reaching the near the energy spectrum, so few times 10 to 15 electron volt. In space, so being able to disentangle each nuclear species, this mission might be heard. There is a proposal for a space mission to be a detector to be placed on board of the Chinese space station. What you really need in this case to reach this goal is to increase by one order of magnitude the exposure of the detector. So we should jump to 10-15 square meters per radian here of exposure. I have no time to go into the details of the detector setting, but the idea is to make it bigger and with better resolution, and to operate this in space, and in particular this will be done on the Chinese space station. So if you increase again the energy, it is very difficult to do this in space. We already saw. You have to rely on indirect measurements. Of course, if you compare the two methods, observing cosmic rays directly in space or observing cosmic rays on the ground, just measuring the secondary particles of the interaction that happened at the top of the atmosphere at roughly 20 kilometers of height, you have different opportunities, but you also have different problems. In particular, if you use indirect measurements, this is the only way to reach the highest energies because of the low fluxes, but you also have to take into account larger systematics coming from our uncertainty on the hadronic models that are on the hadronic interactions, I would say, that are operating in the first interaction, but not only the first, I would say. So for example, just have a look at this plot in the lower left part. This is a sort of measurement of the composition of the cosmic ray beam. So if you have different nuclei, each one with a different mass number, A, and then you take the logarithm of the number and you take the average, and you see that this average as a function of energy is changing. So you start with a relatively light composition around the knee at these energies. This is you can see here the benchmark of different nuclei value for this for logarithm of A. So you start with a relatively light composition here, so and then you see a dominance of maybe heavy components. Then again you have a dominance of light component around the angle, and then we might be dominated by medium mass component, let's say, just before the suppression of the flux at 10 to 20 electron volt. Here, lucky enough, we have a very beautiful detector, which is Auger, the Pierre Auger Observatory, that with its huge surface, more than 3,000 kilometers, is able to measure the energy spectrum very well. And you see that we detected these structures, and the statistical error bars are relatively small unless you reach the 10 to 20 electron volt region. Apart from the energy spectrum, what you can take from the Auger experiment is that the composition is changing. I don't have time to go into the details, but you see here these red curves are the predictions of these observables for protons, while the blue one are the predictions for iron-dominated composition. And you see that the experimental point starts from, I would say, a light composition around the ankle, and then there is an evolution towards an heavy composition. This is even more clear in the right plot. Maybe one of the most important results of these energies was obtained by Auger in this paper. We showed that above a given energy, so above 8 times 10 to 18 electron volt, where the rigidity of particle is such high that the magnetic field does not affect so much the direction of those charged particles. So above those energies with a very large statistical significance, you can see here more than 5 sigma, there is an excess of cosmic rays coming from a direction which is more or less around the anti-center of the galaxy. So it seems that, as expected somehow, above a given energy, the cosmic ray beam is dominated by extragalactic sources, and we see above these energies within the systematics and then, well, within the uncertainties due to the low statistics, we see an excess of particles coming from outside, and we clearly see this anisotropy with a dipolar approximation and a given amplitude. In the future, there is a lot of work on new techniques in order to solve the problem of the low statistics, in order to understand the characteristic of cosmic rays around the 10 to 19, 10 to 20 electron volts energy region. You see here the exposure of the different experiments as a function of time. We currently are operating and relying on the J results, but the new generation experiment we might have, for example, Poema or Grand, will ensure a jump in the exposure. In particular, the Poema mission aims at the observation of cosmic ray showers in the atmosphere, but seen from space, using the fact that cosmic ray showers in the atmosphere produce light, fluorescence light or Cherenkov light. So observing this from space allows you to monitor a huge surface at the same time. Of course, you are very far from the signal. In this case, the signal is very difficult to be detected, and then you have many technological issues, and there is a community which is actually working on solving those issues and designing those missions that would be very interesting in the near future. So my summary is this one. This is the take-home message, I would say. We have a continuous and steady improvement in cosmic ray physics. We have new data, and this new data gave some answers, but also raised new questions because we had many unexpected results and new surprises. So this gives us exciting opportunities and also challenges for our theory colleagues. And of course, both on theory side and experimental side, we need new ideas, because new ideas is going to make the real difference. Thank you very much.
Thank you so much, Ivan, for your overview. We have time for a couple of short questions.
Let me express how grateful I am to Ivan for this review, very, very updated and very extended. The reason is of inviting you is that the dream of Fermi, that the origin of cosmic ray are in the cosmos and related to relativistic effect, are now becoming more and more in reality. We have seen the beautiful talk of Alzen showing the possibility of the neutrino detected could originate from galactic nuclei. But in his lecture also, there were very important results of the anti-coincidence with the J radiation. Let me just go to the key point. The key point is that in the recent months, it has become very clear from a gamma ray burst observation after the first result of Mirzoyan that many possibility of TEV sources occurs in gamma ray burst, many more than what we expected. Therefore, as soon as I realized this, and I had the opportunity to meet Ivan, I invite him to give a plenary, because exactly this region of the TEV has been massively and beautifully mapped from the observation of Dampe, Pamela, and all that. And this review will be, we have record, will be extremely helpful to understand this new science. The only point I'm making is that there is the possibility of a new moment in which the TEV radiation observed by Mirzoyan and many others could be a key for understanding the cosmic ray. Is that the TEV in the cosmic ray? Is that a dream? Well, it's not more a dream, because now I think the majority of people agree that 10 to the 20 electron volt and so forth originate, like we have shown also, from gamma ray bursts. And therefore, it's a new avenue on which I thank very much, and I hope we will collaborate very closely with the NFN on relativistic astrophysics, interpretation of this multi-year effort in cosmic ray.
Thanks for your comments.
Okay, thank you again, Ivan, and let's move to the next speaker, Rahim Moradi, that is going to talk about supernovae and gamma ray bursts, basically.
Can you hear me?
Yes.
Okay, let me share my screen. Okay. Well, thanks. Hello, everyone. In this talk, I will be representing an overview of radiation model and the relevance of the supernova in this BDHN. In this talk, I will focus on the key aspect of the model, because there are many astrophysical and physical model process going on in BDHN. So I will not find time to go through detail, which in principle will take a long time. So I will focus only on the key aspects. This talk is on behalf of large collaboration that has been done part of the work. Okay, first I will talk about the GRB supernova association. Then I will introduce the binary driven hypernova and why the binary driven hypernova was introduced at the first step. Then I will talk about the role of this supernova in the binary driven hypernova and the role of black hole in some type of the binary driven hypernova. After that, the role of the interaction of this supernova with the neutron star in the binary driven hypernova. And finally, I will overview two most recent GRBs that we have studied and represented in by detailed analysis the different episodes of the binary driven hypernova model. So it's well accepted that nearly almost long GRBs are associated with the broad line supernovae, which reveal the common characteristic. When I say common, almost the average characteristic that they show is their optical bolometric luminosity, which is based on the nice review by Kano and his collaborator, 2017. The average of the luminosity observed by supernovae, broadline supernovae associated with GRBs, long GRBs, is around 1.2 10 to 43 erg per second. They show the the kinetic energy almost average around 2×10⁵² ergs, the mass of nickel around 0.4 solar mass, and the mass of ejecta, supernova ejecta, around 6 solar masses, which there are some, these are the average values. There are some deviation from this, as you can see also from this plot. So what makes this special when we go to see the GRBs in this supernovae GRB association? As you can see, the x-axis is the peak luminosity of the bolometric peak luminosity of optical supernovae associated with these GRBs, and in the y-axis, I've plotted the isotropic energy of the GRBs. And as you can see, while their isotropic energy spans from 10⁴ to 10⁵, like 6 order of magnitude, their peak luminosity, optical peak luminosity, remained the same. According to our classification, the one larger than 10⁵ are BDHN of type 1, between 10⁵ to 10⁵² BDHN of type 2, and less than 10⁵ BDHN of type 3, which I will later explain how they will be produced. But were to say that the first one is a binary neutron star black hole, and the others are binary neutron stars. So there is another aspect that when we look at the redshift, there exists till redshift 1, and if there were no optical absorption and we were able to observe the supernova at longer distance, optical supernova at longer distance associated with GRB, but we could span this to higher redshift, but unfortunately there are absorption and we cannot see. Apparently this is the higher limit that we can reach. These are the whole sample that we have collected after many supernova and GRB association. And as you can see, the extended sample almost the same as previous one. It has 9×10⁴ erg per second, the average luminosity, peak luminosity. And for instance, in this tree that in the bold, we have predicted the appearance of supernova, which recently 900114C, yesterday was a nice talk by Elena Pian. She explained how they have observed this supernova peak in this system. Okay, the natural question comes out. Since all these supernova associated with GRBs are broadline supernova and are characterizing, for instance, peak luminosity of around 10⁵, expansion velocity around 0.1 C, and the ejecta mass around 6.7. What is exactly producing the differences in the GRB energetic and their morphology? There are many aspects and role in GRB physics for supernova. The first one, as is very well known, is the role of nuclear physics, which is a production of roughly 0.4 solar mass of nickel, which is the decay of this nickel is responsible for optical supernova, which has been produced through the explosive nucleosynthesis in the initial core collapse in the GRBs. There are other aspects and role of supernova that are many important to be studied. Among them, they create the newborn neutron star, which hereafter I call a new neutron star, out of a core collapse of pre-supernova progenitor star, which I will later on show that they are very crucial for the GRB afterglow emission. And in our model, the trigger of entire GRB process is the supernova. So supernova plays an important role in this model, which in principle produce ejecta, again, 6-7 solar masses in this model, which is crucial for GRB afterglow. Okay. What is binary driven hypernova? Before introduction of this by this model, I think for the first time Rueda and Ruffini introduced the model like IGC model, the name induced gravitational collapse, which later on became the base of the binary driven hypernova. And the motivation was that the existence of broad consensus that GRB progenitor are massive stars, and there is also a broad consensus that most massive stars are in the binary system. So motivated by all this association of GRB, supernova, the binary and massive star, the BDHN model was introduced, which tells all long GRBs are assumed to have a common binary progenitor composed of the carbon-oxygen star of 10 solar mass and a companion neutron star. How this has been created, I will not mention here, but maybe later on the later slide, I will go through it. So different long GRBs have different periods, but these components are the same: supernova, supernova ejecta, explosion, and the companion neutron star. The gravitational collapse of the iron core of the carbon-oxygen star leads to supernova explosion and leaves a new neutron star in the center of explosion, which later on plays an important role in the GRB physics. So right after this CO core collapse and explosion, we have supernova ejecta going through the neutron star mass of around 2 solar masses, and the fallback of the supernova ejecta on the new neutron star, which has around 1.4, 1.5 solar mass. So this is one of the latest result of the simulation of this induced gravitational collapse of the BDHN 1. As I mentioned, why we call BDHN 1, which I will explain more, is that the presence of the black hole in the system after the gravitational collapse of hypercritical accretion of supernova ejecta of the neutron star. As you can see here, the explosion happens. This is on the equatorial plane. The explosion happens. The supernova ejecta goes through the will be accreted by the new neutron star. Neutron star around 25 minutes in this configuration. 21 minutes will collapse to a black hole. And as you can see, fall back on the new neutron star. And this is the side view of this, the same explosion, the same phenomena. In this simulation, the new neutron star mass is, the mass of a neutron star is 2 solar masses. The orbital period is around 5, and the CO star mass is around 6.6 solar mass. Mass of new neutron star 1.8, which around 20 minutes we will have the black hole formation. Okay, this is another aspect of this simulation. The left panel, you can see the accretion to the neutron star, and the right panel accretion on the new neutron star. It's not as such that exactly the energy of the supernova ejecta is fixed, but it will vary. It is varying in a limited range. For instance, here, as you can see, for the lower supernova ejecta energy, we'll have smoother accretion to neutron star, which leads to nearly in the earlier time the collapse of it to the neutron, to the black hole. But as you can see, for the higher accretion ejecta, we can see that it peaks at early time and it goes down immediately, which leads at later time or sometime not having the black hole. So this was the whole overview of the system. So what will happen when I talk about black hole? How this now it's time to talk about how this configuration of the different binary period will lead to the different binary system. When accretion rate onto the neutron star companion is a strong function of binary period. When this binary period is around 5 minutes, black hole smoothly forms, and we don't expect for the significant gravitational emission because it's smoothly formed. This system, when black hole is formed, is called BDHN 1, energy more than 10 to 52 roughly. And the signature of the birth, the moment of the birth of black hole is this jet emission that you can see for several GRBs here, known as BDHN 1. For longer periods, the accretion rate of neutron star, accretion rate of the supernova ejecta onto the neutron star is not sufficient to form a black hole. And we call this system based on the energetic if between 10 to 50 to 10 to 52 BDHN of type 2 and less than that BDHN of type 3. So as you can see, the role of supernova ejecta is very important here. And if we have different configuration, different binary period, we will have different kind of long GRBs with different energy system, energetics. So another aspect of the observation of JEV radiation is that we can estimate, later on I will explain, the mass of the black hole in this system, which for GRB 190114C, the mass of black hole is around 4 solar mass, which is a spin parameter 0.5. And I will talk about the magnetic field and what is this magnetic field, which is 10 to 11 Gauss. Okay, this is what happens when we have accretion to the neutron star, hypercritical accretion onto the neutron star, and black hole forms. This part is for me is the most interesting, not say most, it's one of the interesting aspect of BDHN. When we have the neutron star and the accretion of supernova eject on it, this and black hole form, black hole inherits the magnetic field of the neutron star. So this magnetic field, together with the material around the black hole and the black hole itself, Kerr black hole itself, will produce a configuration we call it the inner engine of the system. This inner engine, to shortly say, and I will expand it in the next slide. This is the part that is responsible for the what we call prompt emission, GRB prompt emission, or ultra-relativistic prompt emission. How it will happen is that when we have this rotating Kerr black hole in this magnetic field, there will be some effective charge, not charge. I insist that there will be some effective charge that will produce, since this magnetic field of the neutron star is around 10 to, will be amplified to more than 10 to 14 Gauss, this will produce some overcritical field around the black hole, which in turn will produce some E plus E minus. This E plus E minus is optically thick, and that problem of compactness, it expands, and at around 10 to 11, 10 to 12 centimeter, we will have the radiation in the MEV, which is radiation in MEV, which is called ultra-relativistic prompt emission phase. Why ultra-relativistic? Because this shell needs to expand in a highly relativistic regime to be optically thin at around 10 to 11 centimeter. So after that, we will have the configuration for producing the JEF emission, as you can see here, these are the pitch angles of the electron that can produce the JEF, and as you can see, it's around 60 degree, the half open angle of 60 degrees that can produce kind of jetted JEF emission. Okay, what we can learn from the black holes in this BDHN model is that, as obvious, they are not the Kerr black hole in this system is not in a stationary space-time, is not in vacuum, and is not asymptotically flat. In turn, this system is endowed with a parallel magnetic field parallel to the rotation axis of the Kerr black hole. It has no electric charge, but the gravitomagnetic interaction between the black hole angular momentum and the surrounding magnetic field induces an electric field, which can be viewed as an effective charge. If I want to say with more beautiful words, is like a natural selection that universe is selecting to prevent having a charged black hole. Already this effective charge is Q over M is around 10 to minus 5, so it's not a significant charged black hole. But GRB prompt emission phase is produced in order to prevent this charged black hole. So, and finally, they are not asymptotically flat. They are embedded in a low density, the fully ionized plasma, which is essential for this electrodynamical energy extraction process. And thanks to the extractable mass that has been introduced by the irreducible mass formula of Christodoulou-Ruffini, the Kerr black hole in principle radiate for infinite time, and the luminosity, the JEF luminosity, follow power luminosity, which this alpha of JEF is around 1.2, the average in this one. And when we take the average, is around 1.2 for almost all the long GRBs that show the JEF emission. This JEF emission is in a conical region of 60 degrees around the black hole axis, and this in view of presence of a low density plasma, they cannot emit continuously. They emit in each fraction of time. They can accelerate some particle and then starting over again and using this rotational energy. So this mechanism has not been only used for GRB, also for when we rescale for active galactic nuclei, which they can have the mass around 10 to 9 solar masses. This has been published for the case of AGN, also by Rueda and Ruffini, 2020. Okay. Now let's go back to new neutron star. What happens for new neutron star? There are two things in work for the new neutron star, is that when we have fallback to neutron star, neutron stars start to spin up. Then at the same time start to have the radiation in the multipolar radiation. As you can see for p orbital, when we have black hole formation around 5 minutes, after 30-40 minutes of the supernova explosion, it will spin up to 1 millisecond pulsar, which this 1 millisecond pulsar is necessary to explain, which will create a triaxial configuration, which is necessary to explain the neutron star rise occurring in this system, which happened around 30 minutes after the supernova explosion.
Raim, 5 minutes.
Okay, so I will go. After here you can see the afterglow. The afterglow of the GRBs in this model. So it's based on the new neutron star eject electrons to the supernova ejecta. There they can gain also some kinetic energy of the supernova ejecta, and there they can produce synchrotron radiation. At later time, the multipolar radiation is dominant, but at early part is the kinetic energy of the supernova is dominant. So all the X-ray afterglow of the radiation have the average luminous, the average power law is 1.48 plus minus 3, and this is well characterizing the new neutron star behavior, characterized by new neutron star behavior. Actually, this power law is the backbone of GRB, which almost covers all the GRB history. So since this all radiation have X-ray afterglow, this X-ray afterglow implies that it emits spherically or at the quasi-spherical emission. This is the first example that I want to briefly show that how after the detection of this GRB, we were able to, by time result analysis, we were able to notice different episodes and different physical processes undergoing this GRB. First, we have the rise of neutron star, which that story I said in the previous slide, that is a spin of the new neutron star because of the accretion and the dipole radiation. The second part is the ultra-relativistic prime phase, which we characterize by the presence of the black body in the Fermi GBM data, because we need to find a black body to explain this ultra-relativistic expanding shell, which thermal radiate at around 10 to 11 centimeter away from 12 centimeter away from the central engine. The third part is the cavity. Cavity first is carved out by the black hole formation after the neutron star collapse to the black hole, then depleting more by this expanding shell, many expanding shells that reach to the 10 to 11 centimeter. So then there will be some part of this shell going inside the supernova ejecta. Their reaction and they bouncing back create this cavity radiation. Then they're expanding inside the supernova ejecta, which promote the supernova to the hypernova, produce this hard and soft X-ray flare. This is the JEV radiation, which is produced by the black hole activity, and this is the X-ray afterglow, which is produced by the new neutron star activity, and recently Hess observation, which we explained by the glitch in this highly rotating neutron star. And you can see the mass of black hole in this system is 2.32 solar mass, spin parameter 0.27, and the dipole magnetic field on new neutron star is 410 to 33 Gauss, and new neutron star initial period obtained from data is 1 millisecond, in agreement with all.
Massimo, there is a technical problem. Maybe we see.
Okay, let me share again because Can you see?
Yes, yes. So we can see.
Okay, this is back. The final slide I wish. So after having this, after having the redshift, we immediately calculated the energy, which was as more than 10 to 52. The energy was 10 to 53, and we predicted the supernova bump should be around from 14 to 21 days, which was indeed confirmed by Melandri et al., which yesterday by Elena Pian was extensively represented this supernova observation. So, and as you can see, these are the part of optical rise of the supernova. This is the X-ray afterglow, which we have submitted work explaining well the UPE physics, ultra-relativity prompt emission phase, and we have represented other part in the recently published paper. And the final simulation is the synchrotron radiation, which is powered by new neutron star, and expanding supernova ejecta, which is really essential for this supernova. As you can see, synchrotron radiation will explain different energy bands from X-ray, optical, and the radio in this GRB. Okay, so the role of new neutron star synchrotron radiation as I said, is a backbone of the GRB, dominates entire the history of GRB, starting from the rise of neutron star to the latest emission at 10 to 7 seconds or later. So thanks to this going down the rotational energy of neutron star, we can see finally the rise of optical supernova. And the spin-up the supernova is essential to relate the afterglow of supernova explosion followed by hypercritical accretion onto neutron star, and the first clearly identifiable the significant energetic signal of the GRB. So I close my talk by this conclusion. So GRB not only are the most energetic and powerful sources, but also are among the most complex ever systems in the universe, which really offer unprecedented challenge for human understanding. Guided by this 50-year light observational multivariate from radio to all the way up to the TEV emission in the history, it has been possible to formulate a new paradigm and identify new physical and astrophysical regimes in this system. Finally, comprehension and identification of new physical law, both in the quantum and classical relativistic regime, is allowing to make understandable and astrophysics of the astrophysics of black hole, neutron star, and supernova in GRBs and AGNs, and achieve one of the developing, expanding frontier of the scientific knowledge. And from what we are seeing in this interesting MG16 meeting, from the exciting FAST and SKA activity and from the theoretical progress in the understanding of dark matter, new astrophysical companions are joining the GRB and make this journey much exciting and add momentum to expanding the frontiers of scientific knowledge, namely the fast radio burst and also the new understanding of the nature of the galaxy textures in our universe. Thank you.
Okay, thank you, Rahim. We are 10 minutes later, so I take only one question if there is any, or I will, no questions? Okay, thank you again, Rahim. Now we move to the last speaker of the session, Giancarlo Cella, that he is going to talk about recent observation of gravitational waves.
Okay, thank you. I'm trying to share my screen. I hope you can see it and I hope you can hear me. Yes. Okay, so I will report about two events that has been found by the LIGO-Virgo collaboration recently, actually in a very short time span, because they were separated by just 10 days, one from the other. And as I will say, this is the first solid evidence for a new kind of binary system coalescence, namely the binary system coalescence of a pair composed by a neutron star and a black hole. Before entering directly into this, I will give you some context. The LIGO-Virgo collaboration started since a long time to make this kind of observation, and to the present, the only kind of sources that has been detected were binary coalescences. The first one was also the first direct detection of a gravitational wave. It was a coalescences between a couple of black holes. The second one, more or less 2 years later, was a coalescence of two neutron stars. And the pair of events that I will discuss today was just what is leaking from this scenario, a mixed pair between a neutron star and a black hole. you can, just to have a bit of context, you can see in the picture on the right the currently confirmed events that the collaboration has detected. The plot is a plot which is ordered by choosing two important parameters, which are the mass ratio between the two objects which compose the pair and the chirp mass. One observation which is important also for the following is that if you look at this picture, you see that in some sense we are able to constrain very well the chirp mass, and the reason is that chirp mass is the key parameter which determines, starting from the lowest order in a post-Newtonian approximation, the shape of the gravitational wave signal in the in-spiral phase. So it is very well determined. On the contrary, the mass ratio has a large uncertainty because enters in the shape of the waveform only in the higher order correction. Anyway, you can look at this scenario for the detection. There are the plot is divided in several zones which depend on the kind of pair. As I said, there are in green the zone in which the pair is most probably black hole coalescence. The red zone is the region in which we have a pair of neutron star, and the region which is of most interest today is the yellow one, in which you have a neutron star black hole. Okay, why this kind of detection can be in principle interesting for us? And this will be discussed in the following. And also I plan to discuss how much we are confident about this detection that we did, what we have learned from this particular couple of events, and also at the end I will give a bit of information and speculation about what we expect to learn in the future with the future scenario of observation. Anyway, this is the same collection of events from a different perspective. It is a more qualitative. You can just see both the progenitors and the final object. And this is essentially sorted in terms of the mass of the object. So if you look in green, you see the couple of binary neutron star coalescence that has been detected until now. There is a population of neutron star and also black hole which have been detected not by gravitational wave but from electromagnetic observation. And we have also the large number of binary black hole coalescence I showed you before. The couple of events that I will discuss are shown in this plot, evidence in white. And you see that essentially, qualitatively, the evidence is that one of the progenitor, the secondary mass, is essentially inside the expected region from the masses of neutron stars, and the other is in the region of black hole. This is not the first evidence that we had during this, looking at the data obtained by in the third observing run. There is another event, for example, which is the one I show you in orange, which from the point of view of the parameter and masses of the components is very well inside, can be interpreted, is much similar to the GW 2115, so it could be well also a binary black hole neutron star event, but has a very low significance from a statistical point of view. So we are unsure about the fact this is a real event or could be also simply an artifact. The other object, which is similar and can be interpreted as in principle as a black hole neutron star, is GW 19814. This is real because it's very loud, but the secondary mass is quite large for a neutron star. And probably it is most probably a black hole coalescence with a very light black hole progenitor. What is the some basic information about our collaboration? Currently, our collaboration is composed by LIGO, Virgo, and also Kaga in Japan. These are the location of the interferometers in red, which are from the LIGO collaboration. Virgo is, as you know, in Italy, and Kaga is, as I said, is in Japan. Currently, the sensitivity of Kaga is not yet large enough to give a significant contribution to detection and parameter estimation. The events I showed you before comes from 3 data taking periods that are shown here in the plot. And we ended the last one, as I said, was the O3 run. And we are just finishing to analyze and to classify the data for the first part of this O3 run. We are currently starting to analyze the second part of this O3 run, and in particular, the couple of black hole neutron star events I'm discussing comes from the second part. This is important from the point of view of the significance, because as I will tell you immediately, it is not so, at least for the first event, it is not trivial to establish what is the statistical significance of this kind of events. If you look at the time frequency plot, which represent the data that we used to detect this event, you see that there is a first important difference between the first one. Sorry again, just a second. Okay. The first one, in the first detection, the first event we are discussing, one of the 3 detectors, namely the Hanford LIGO detector, was not operative. So we got signals only from Virgo and Livingstone. And if you look at the time frequency plot for Livingstone, you can see clearly a signature of this event, which is the expected excess of energy, which represent the way in which near the coalescence, the dominant frequency of the chirp signal change with the time. There is no such kind of evidence in the time frequency plot for Virgo, and there is no direct evidence for this in the time frequency plot for the second event for all the 3 detectors. This, of course, do not mean that the event is not significant. It only means that this particular event is very low in Livingstone. The last comment about this slide is that in both cases, Virgo was not sensitive enough to give a trigger for the detection. So in the first case, it was just a single detector detection. And in the second one, it was a 2 detector detection. Of course, this is only about the issuing a trigger for the event, because parameter estimation is a very different issue. And when we move to parameter estimation, we use also the data for the detector which was not significant enough to give a trigger, and they can give and have given a relevant contribution to the parameter estimation, as I will show you in a moment. So about the significance, the problem here is that in principle, if the noise is the theoretical noise which you can found described in statistical text, namely a Gaussian process, the significance could be completely described by the signal to noise ratio of the event. But the real noise of our detector is not really Gaussian, is not really stationary. So assessing the significance of an event is more complicated, require a more complex effort. And the basic idea is to add more consistency test. Do not look only to the signal to noise ratio, and when possible, to use coincidence. Now, I mentioned it before the GW 190426, which is from the point of view of the parameter, a good example of black hole Newton star event. But if you look in this plot shows you essentially the density of probability, the logarithm of the probability density of the trigger in trigger events triggered by noise only. You see that in this case, the two events, the two triggers for this kind of event was very inside the region in which there was quite high background. For the GW 000115, which is the two detector trigger event, we are still inside the region in which there is some contamination of the background, but the situation is considerably better compared with the 19426. And additionally, we have the possibility to use the fact that we have two triggers, and so we can use coincidence to improve a lot the significance of the statistical significance of the event. And finally, for the single trigger event, which is this one, the situation is a bit different because we have just a single trigger, so we can't use coincidence. But on the other hand, you can see that the single trigger is well outside the region in which there is a significant contamination for the background. And this makes us quite confident that also this single detector event is a real event. However, if you try to quantify this, for example, evaluating the false alarm rate of the detected event, you can do this quite easily for when you have a couple of events. So there are several reasons. One is that when you do a coincidence, you are suppressing non-Gaussianity of the noise of the detector. And so in this case, you can confidently estimate the false alarm rate, and a conservative estimate in this case is of one event in essentially 200 years, which is quite satisfactory. On the other hand, for the single detector event, it is not at the moment easy to give a reasonable estimate. We have to look only to the amount of data that we used for the measurement, and we are still not finished to completely look at all the data that we have, so the situation will change in the future. So in this case, a reasonable estimate for the false alarm rate is give a higher number, which is about 1 in 3 years. But for the reason I give you and discussed with you before, anyway, we are quite confident also about the fact that this is a real event. Of course, when we will move on in analyzing all the data for the second part, and we will be able to give a more refined estimate of the background, this estimate can change a bit. Why these kind of events are potentially interesting? Well, in principle, we can learn a lot about the analysis of this. For example, in principle, we can have access to information about the equational state of neutron star. We can have information for the nucleosynthesis process, and also about we can obtain directly a rate, an estimate for the rate of expansion of the universe. Note that in both of these two cases, we need an electromagnetic counterpart. Next, by looking at these events by itself, essentially by looking at the masses and the other parameter that we can extract from the data, we can improve our knowledge about the NSPH event rate and NSPH pair population. And this can give you useful information to understand what are the formation channels that give rise to this kind of pair. Now, what are our constraints at the moment? The constraints are connected to the kind of sensitivity of our detector in terms of observable frequency. And so essentially, the first point that we have to keep in mind is that we are able to observe only the last part of the spiral phase, which, depending on the mass of the pair, can be between maybe 10 to 100 seconds. Also, the signal which is emitted in the merger phase, which, by the way, is the signal which contains the most important information about, for example, equational state, is in a region which, in a high frequency region with respect to our detection band, in which we have not, it is not the much sensitive region for us. And also, we have to take into account, I will discuss a bit this later, that the direct signature of neutron star can be small. This is not necessarily true, but in order to see a good and low signature for neutron star, we need some peculiar condition in terms of masses, for example. About the localization, which is important for searching for electromagnetic counterparts, for example, we see that for the first event has a quite large indetermination in the area in the sky in which we can localize the event. There are a couple of numbers. The first refer to the first fast determination of the localization, which is done in a not completely inaccurate way in order to be fast, in order to give a fast notice to the astronomical and astrophysical community. The situation is much better for the second event, and in this case, the reason is that in the first case we have only a couple of detectors that we can use for determining the position. In the second, we have 3. But in both cases, we found no evidence of an electromagnetic or neutrino counterpart for this kind of event. And there was several attempts, roughly about several tenths of circular has been delivered about searches, but no evidence for electromagnetic counterparts has been found. Coming to the masses of this object, in this table, you can see the determination for the main parameter and for the masses in particular. For the masses, you can look also at the right plot, and here you can recognize what I anticipated before. We have a large indetermination on the mass ratio, which corresponds to the inclination of this line, and a good determination of chirp mass, which corresponds to this kind of hyperbola. And an important point to notice here is that there is no overlap between the masses of the first and the second event. If you look at the spin, you see that for the first event, I have not time enough to explain in the detail the parameter, but in this kind of plot, you have a density which corresponds to the probability density of having a given magnitude and inclination with respect to the angular momentum of the pair. And you see that in the first case, we have for the primary component, which is the black hole, evidence for a quite small spin in amplitude and no relevant information about the direction of the spin. While, and this is true in both cases, for the second progenitor, secondary spin, which is the neutron star, we have a large indetermination. Essentially, we have no good information about the spin of the neutron star. And this is expected because the determination of the spin by looking at the signal is enhanced for the member of the pair with the larger mass. The determination of this spin is important because, for example, the component of the spin parallel to the angular momentum is important because give a contribution to the phase evolution in the spiral phase, and so it can be determined with looking at the waveform signature. The perpendicular component is also connected to the waveform signature, but not by the way of the phase evolution, but because it can induce precession effect.
Giancarlo, 5 minutes.
Yes, sure. In the second case, we have a mild evidence for an anti-aligned spin. Looking a bit better to the information that we can extract. Of course, the first thing that we can do is to extract an estimate for the NSBH merger rate. We did this using several assumptions. The first estimate uses only these couple of events. In the second case, which give a more optimistic estimate, we consider not only these couple of events, but also all the subthreshold event of this kind in the relevant mass range. Of course, this is just the start of a process that will improve in the future when we will see much more events of this kind. But this is important because now we have an estimate for all the possible pair of compact objects, and this is the starting point to have coherent information to deduce information about, for example, the story or the formation of this object in the population. Maybe I can skip this. An important point is about the direct evidence of neutron star. As I said, special conditions should be fulfilled in order to have a direct evidence of a neutron star. We can, for example, look at and try to determine the deformability parameter of the neutron star. This can be measured essentially in the inspired phase by quantifying the ratio between the quadrupole momentum induced by tidal forces and the tidal force themselves. And it comes out that this is something that can be very small when there is a large asymmetry between the masses of the two objects. It is not difficult to understand this because the Marial force scale with the cube root of the mass of the black hole, while the the scale of the inner stable circular orbit scale with the first power of the mass of black hole. So typically when the black hole is large, the neutron star will be swallowed entirely by the horizon before being able to be disrupted. And in fact, if you use the data from this couple event to try to find some constraint on this deformability parameter, you see that essentially you have no information using this. So no direct evidence of a neutron star, but we have just using the fact that the masses are in the correct and expected interval to be, and of course this means that in principle more exotic interpretation for the lower mass object are possible. Why no electromagnetic counterpart? There were, as I say, there were several observations, but no electromagnetic counterpart, and this is expected. First of all, as I said, there is a large mass, too large mass asymmetry, so no tidal disruption is expected. And note that anti-aligned spin suppress disruption, and we have a mild evidence of anti-aligned spin. These events are far from us, 7 times the first neutron star pair coalescence that we get. And also, as I show you, there is a large uncertainty in localization. And this will reduce the chance of a positive electromagnetic follow-up. However, some improvement are expected when we increase in the near future, we will increase the sensitivity. The event rate will increase, and so it will be possible to better explore the large space of events for this kind of events. And also for the louder events, we will be able to improve the localization. Conclusion, we observed two coalescences which are consistent with neutron star black hole binaries. We have not a direct signature for this, but strong hint coming from the value of the secondary mass, which are consistent, for example, with the galactic neutron star population. Also, primary masses of the black hole companion are consistent with the formation scenario. No electromagnetic counterpart, but this is not surprising. And I had no time to discuss this, but the rate estimate is consistent with several formation scenario. So we have consistency, but not yet the capability of put constraint on several different hypotheses for the formation scenario. We are still analyzing O3 data, and soon in next year, the O4 run will start with an improved sensitivity. And as we expect, the event rate will scale accordingly. Most optimistically, we will get a factor 8 in the event rate. So stay tuned for further event of this kind. Thank you.
Okay, thank you so much, Giancarlo, for your overview. I see a question in the audience.
I have a question.
Wait. First, there is a Jorge that is want to ask him something.
Okay, then I will say something at the end.
Okay.
Thanks, Massimo. Yes, I have written the question, but thanks for
yes. Okay.
But yeah. So I am a bit confused because you say that you consider these detections as solid and confident, that you are confident. But in your slide number 6, you show the false alarm rates, and these are huge. I mean, the time that you get to get a false alarm is even shorter than the observing run. So I don't know how you can consider this as solid or confident. Can you clarify, please?
Yes. The main, I will distinguish between the two events. For the second event, the false alarm rate is not so large. So in this case, I think we can confidently say that this is a solid event. In the first case, the problem, as I said, comes from the fact that it is difficult, and maybe this will be improved, to give an estimate of false alarm rate based on the data that we were able to analyze until now. So your observation is correct. Essentially, the false alarm, if you look simply at the false alarm rate, the false alarm rate is just comparable with the inverse of the observing time. And this is the better we can do at the moment. On the other hand, we have int, which comes from looking at the characterization of the noise, that these events can be considered solid. But this is something that will evolve, I mean, for the first single detector event, when we will be able to improve our description of the background. So I will say, for sure, the first event is solid also, sorry, the second event is solid in terms of false alarm rate. The first is, we have some evidence that we make us thinking that it is real. But if you look to a characterization in terms of false alarm rate, we have still to improve the estimate of the background.
Thank you.
Okay, Remo?
Well, I am puzzled about the many points, but I read in your paper, which is subscribed by 54 groups only in Italy. These represent the first confident observation to date of neutron star black hole binary via any observational means. I would like just to stress that there are, by this time, many hundreds of binary systems, some with black hole and with all the tail of a neutron star in GRB, and ranging from electromagnetic to in all wavelength and so forth. Therefore, I think this is not a proper statement. The second point instead is more precise. I mean, with respect to other cases, since the Misner-Weber to the 1509-14, there has been a very important point that the data were very clear. And this has been very, very important because it was possible to show that these data were not in agreement with basic physical law. And this has been published. And similarly, in the source 170817, there is the gravitational wave and the GRB. The situation has been very interesting since the last Grossman meeting and the previous one in Rome, where we had so interesting discussion. And right now, the situation is clearing up. And we can present some alternative point of view even in today's talk, in today's round table. What I'm really concerned is that in the present case, the data are not comparable either to the Weber data or to the 150914, nor to the 17017. Therefore, I urge you to try to improve the quality of the data, the statement, in order we can submit every source to an analysis with the fundamental law of physics. I thank you anyway for the effort in the presentation.
Thank you.
Okay.
And maybe before closing, I would like to show this poster, which we will finalize in the forthcoming day, the Italian meeting.
If you can wait a second, I have a question myself for Giancarlo. In one of your last slides, you were showing why we don't see an electromagnetic counterpart. And you basically show a couple of theoretical explanations for that. I'm considering if maybe the best explanation is an observational bias, because actually the poor localization was an area that was 10 times as large as the one of the so-called kilonova event. So I don't think that we need a theoretical explanation to explain why you didn't observe the electromagnetic counterpart.
Yeah, that's true in the sense that in any way, also if there will be one, it would have been very difficult to see it. Anyway, I just included it before because this gives you an idea that also when we will be able to constrain better the sky localization, there will be a class of coalescence of this kind that probably will not have electromagnetic counterpart by itself. But you are right. Basically, at the moment, there is this observational bias.
Okay, Remo, your poster.
This was exactly my point, that in the previous case, we had good enough data, Weber 1517, to compare with fundamental law of physics. And in this case, this is missing at the moment. But I wish they can improve in the way that we can make this comparison necessary and stringent.
Yeah,
Remo,
sure.
the poster.
The poster. We have MG16, and we have a certain number of, as usual, of satellite meeting. The next satellite meeting will be August 6, 2021. And we are going to circulate the poster soon. We will have also other meeting following satellite meeting, following once a month in Central Asia, in South America, and so forth. Therefore, we will make known as soon as the poster will be ready. Thank you very much, everybody. It was very exciting. It was a very, very exciting morning, and let's continue in the afternoon at 15:30. Thank you.
Thank you. Thank you so much, all the speakers, and good afternoon.
Thank you all. Good afternoon.
Thank you. Bye.